Hello there, and welcome to the Serene Scroll. I'm so glad you could join me tonight. Perhaps it has been a long day, full of details and demands, but all of that can now fade into the background. Here in this quiet space, there is nothing for you to do but rest, to breathe, and to allow your mind to drift. And just before we begin our journey into the quiet wonders of the universe, if these quiet explorations help you unwind or bring a sense of peace to your evening, consider gently tapping the like button and subscribing to the channel. It allows us to continue creating these moments of calm for you. Tonight, we begin a new story, a journey into a world hidden just beneath the surface of our own. Imagine for a moment a master cartographer. For centuries, this cartographer and their predecessors have been working on a single magnificent map of reality. It is a masterpiece of exquisite detail and profound logic. Every river flows predictably to the sea. Every planet follows a graceful, calculated arc across the heavens. This is the universe as a grand and beautiful clockwork wound by an ancient hand and left to tick along in perfect, knowable harmony. Given the position and momentum of every gear and every spring, you could predict its state at any moment in the future and deduce its state from any moment in the past. This map, the map of classical physics, brought a deep sense of comfort and order to the world. It whispered that everything from a falling apple to a distant star was governed by the same elegant, unbreakable rules. There were no hidden corners, no uncharted territories of mystery. The map was almost complete. All that remained was to fill in the final tiny details. But it was in those very details that the magnificent map began to unravel. The cartographers, seeking to perfect their work, turned their attention to the smallest scales imaginable. They wished to map the continents of matter itself, the tiny fundamental islands we call atoms. According to the map's own rules, an atom should be like a miniature solar system. At its center, a heavy nucleus like a sun, and orbiting it much lighter electrons like planets. It was a beautiful, simple image, and it seemed to fit. But there was a ghost in this machine, a fatal flaw in the drawing. One of the most fundamental rules on the cartographer's map stated that any charged particle moving in a curve like an electron in orbit must continuously radiate away energy like a tiny lighthouse spinning its beam. Following this rule, the electron planet should be losing its orbital energy with every turn. Its path should not be a stable, peaceful orbit, but a death spiral. In less than a trillionth of a second, the electron should lose all its energy and crash into the nucleus, annihilating the atom in a tiny puff of light. If the cartographer's map were true, the very chair you are resting on, the air you are breathing, you yourself should not exist. Every atom in the universe should have collapsed into a whisper of energy an instant after it was formed. Yet here we are. The world is stable. Matter is solid and enduring. The cartographer stared at this paradox. The map predicted collapse and ruin, but the world itself hummed with quiet permanence. It was as if they had drawn a map of an island that by all the laws of geology and oceanography should have sunk beneath the waves eons ago. And yet there it was, lush and real, defying the very ink and parchment that sought to describe it. Puzzled, the cartographer set aside the problem of the impossibly small and turned to another frontier, the intensely hot. They sought to map the light that pours from the heart of a forge or the belly of a star. This phenomenon, known as black-body radiation, seemed simple enough. Any object, when heated, begins to glow. First a dull red, then a brighter orange, then a brilliant yellow-white, and finally a searing blue-white. The color of the glow depends only on its temperature. It's a universal language of heat, spoken by everything from a glowing coal to a distant galaxy. The cartographer's task was to create a line on the map that could predict the exact brightness of every color in that glow. The classical rules, so successful everywhere else, offered a clear prediction. But when the cartographer drew the line according to these rules, the result was monstrous. For the gentle, long wavelengths of red and yellow light, the map worked perfectly. But as the wavelengths got shorter, moving towards the blue, the violet, and then the ultraviolet light, the map's prediction soared upwards unchecked. It predicted that a simple warm object should be pouring out a staggering infinite amount of energy in the form of ultraviolet light. If the map were true, lighting a simple candle would not produce a gentle flame. It would unleash a catastrophic blast of high-energy radiation, an ultraviolet catastrophe, that would vaporize everything in its vicinity. The very act of being warm would be an act of cosmic violence. Once again, the territory refused to match the map. We can sit by a warm fire without being annihilated. The universe is not awash in this impossible searing light. The real world glowed gently, modestly, its energy peaking in the visible spectrum, and then fading away quietly in the ultraviolet. The map predicted an infinitely tall mountain of energy, but reality showed only a gentle hill. And so, the master cartographer was left in a state of profound humility. Their beautiful clockwork map of the universe, a source of certainty for generations, lay before them with two glaring impossible flaws. At the smallest scales, it predicted a world that would instantly dissolve. At the highest energies, it predicted a world that would violently explode. The map was not just incomplete, it was fundamentally wrong in these new territories. The smooth, continuous lines that described the orbits of planets and the rolling of hills simply did not work here. Something was profoundly different about the fabric of reality at these extremes. The problem was not the drawing, it was the language of the drawing itself. A new cartography was needed, built on entirely new principles. The first clue to this new language did not come from redrawing the lines, but from a revolutionary idea about the very ink itself. An idea that perhaps reality wasn't a smooth, continuous flow, but was instead made of something granular. It was as if the world at its most fundamental level was written not in a continuous stroke, but in tiny individual dots of existence. A world made not of waves, but of grains. Our journey begins not with a flash of light, but in the deep, quiet darkness of a simple, heated object. For centuries, the world of physics felt like a perfectly calm, predictable sea. Everything flowed. Energy was seen as a continuous wave, a smooth and unbroken current. If you wanted to warm a room, you could add any amount of heat you wished. If you wanted to move an object, you could apply any amount of force from the faintest touch to a powerful shove. Reality, it seemed, was a gentle, continuous ramp. You could stand at any point along its slope. There were no forbidden places, no gaps in the fabric of what was possible. This view was elegant, comfortable, and it worked beautifully for almost everything we could see and touch. It built bridges and powered engines. But as the 19th century drew to a close, a tiny, stubborn crack appeared in this perfect facade. It came from studying something as simple as the glow from a hot piece of metal. When physicists tried to create a theory to describe the colors of light, the energy that such an object should emit, their equations broke. The theory predicted that a simple warm object should be radiating an infinite amount of energy, especially in the higher frequencies of ultraviolet light. This was, of course, impossible. Our world is not bathed in infinite searing energy. The theory was elegant, but it was profoundly wrong. This quiet failure was nicknamed the ultraviolet catastrophe, a gentle name for a deep crisis that suggested our understanding of energy itself was flawed. Into this subtle confusion stepped a German physicist named Max Planck. He was a conservative thinker, not one to tear down the old structures of science. He tried for years to fix the equations within the old rules, to patch the crack without rebuilding the foundation. But nothing worked. Finally, in an act he later described as one of desperation, he tried a strange, almost illogical idea. What if he wondered energy wasn't a smooth, continuous flow? What if it couldn't be divided into infinitely smaller and smaller amounts? Imagine again that smooth ramp of reality. Planck suggested that perhaps it wasn't a ramp at all. Perhaps it was a staircase. Let this image settle in your mind. A staircase. You can stand on the first step. You can stand on the second step. With a small effort, you can move from one to the other. But what you cannot do is stand in between the steps. There is simply no place there to put your foot. The space between the steps is forbidden territory. Planck proposed that energy worked in exactly the same way. An atom, he suggested, could not absorb or release just any amount of energy. It could only do so in specific discrete packets, like taking one single step up or down the staircase. He called one such packet, one indivisible step of energy, a quantum. This idea was bizarre. It felt unnatural. It was as if you could only fill a glass of water with one specific scoop at a time, and never with a continuous pour from the tap. Planck himself was deeply unsettled by his own discovery. He thought it was merely a mathematical trick, a temporary fix that would eventually be replaced by a more sensible, continuous explanation. But the trick worked perfectly. His new equations, built on the idea of these energy steps, precisely predicted the light from a heated object and solved the ultraviolet catastrophe completely. The smallest possible change in energy was no longer zero, but one single quantum. And the jump from one energy level to the next, that little hop from one step to the ineffable next, came to be known as a quantum leap. In our common language, a quantum leap has come to mean a huge dramatic change. But in its true physical sense, it is the smallest possible change there can be. It is the fundamental grain of action in our universe. For a few years, Planck's idea remained a clever but strange footnote in physics. It was a fix, but no one knew what it truly meant. Was the universe really built on a staircase? Or was this just a useful story? The answer would come from another young mind, one who was comfortable with revolutionary ideas, Albert Einstein. Einstein was thinking about a different puzzle, a phenomenon called the photoelectric effect. It was a simple observation. If you shine a light onto a piece of metal, sometimes it will knock tiny electrons loose, creating a small electrical current. The old theory, where light was a continuous wave, made a clear prediction. A brighter light, being a more powerful wave, should knock electrons out with more energy. A dim light might not work at all, but if you made it bright enough, It should always be able to free an electron. But that's not what happened. Experiments showed that a very bright red light, no matter how intense, could not free a single electron. Yet a faint, dim blue light could do the job instantly. It was the color of the light that mattered, not its brightness. Imagine the surface of the metal is covered in tiny bells, the electrons. The old wave theory of light is like trying to ring them with a slow, steady push. You can push harder and harder with a brighter and brighter light, but you'll never make them ring. Einstein, inspired by Planck's quanta, suggested a different picture. What if light itself wasn't a continuous wave, but a stream of tiny individual particles, little packets of energy? He proposed that a beam of light was more like a shower of tiny grains, which he called photons. The brightness of the light was just the number of grains being thrown per second. The color of the light was the energy of each individual grain. A red light in this view is a shower of low-energy grains. You can throw millions of them, but not one has enough of a punch to knock an electron free. A blue light, however, is a shower of high-energy grains. Even a single one of these blue light photons, one tiny grain of light, carries enough energy to strike an electron and send it flying. With this one beautiful idea, Einstein showed that Planck's quanta were not a mathematical trick. They were real. Light itself, the most fundamental wave we knew, was grainy. Energy came in indivisible parcels. The universe at its most intimate level was not a smooth ramp. It was a staircase built from countless tiny definite steps. And so the first pillar of this new reality was set. The continuous flowing world of our senses began to dissolve, revealing a hidden, stuttering, granulated reality beneath. It was a profound shift in our perception of everything. But in solving one mystery, this discovery opened the door to an even deeper one. For centuries we had proven that light behaves as a wave. It bends around corners. It spreads out in ripples. It interferes with itself, just like waves on a pond. How could it possibly be both? How can something be a smooth, continuous wave, and at the same time a tiny, discrete particle, a single grain? It seems like a contradiction, a paradox that cannot be resolved. Yet it is here in this very contradiction that the true heart of the quantum world begins to beat. It is not a choice between one or the other, but an invitation to see that reality might just be both at once. The tidy, predictable world of classical physics, that calm and continuous sea, was beginning to show ripples. The discovery of the quantum, the idea that energy comes in discrete packets, was the first stone cast into its quiet waters. But this was only the beginning. The next revelation would not just create ripples. It would reveal that the very substance of reality itself was something far stranger, far more fluid and mysterious than anyone had ever dared to imagine. To understand this, let us perform an experiment in our minds. It is a simple setup, elegant in its design, yet it holds within it one of the deepest truths of our universe. Imagine a blank wall, a canvas waiting for a story. In front of it, we place a barrier, a simple screen with two thin parallel slits cut into it. And on the other side, we have a device that can fire tiny particles one by one, like a child throwing grains of sand at a fence. First, let's imagine we are firing those grains of sand. Each grain travels in a straight line. It will either be blocked by the barrier, or it will pass through the left slit, or it will pass through the right slit. If we let this run for hours, what pattern would we expect to see on the wall behind? It is simple, intuitive. we would find two distinct piles of sand, each one a fuzzy line directly behind one of the slits. The story on the wall would be a clear and direct account of the paths the sand took. This is the world of particles, a world of definite objects in definite places following definite paths. Now let us change the story. We will keep the same stage, the wall, the barrier, with its two slits. But this time, we will replace our grains of sand with something far more fundamental. We will fire electrons. And to ensure there is no confusion, no possibility of them bumping into each other and complicating the picture, we will fire them, one by one by one. An electron leaves its source. A moment later, it strikes the wall. Then another is fired, then another. We let this happen thousands, millions of times in the quiet dark. Each electron a solitary traveler on its journey. Common sense tells us what we should find. An electron is a particle, a tiny dot of matter. So just like the sand, each electron must pass through either the left slit or the right slit. We should therefore end up with the same pattern, two distinct lines on the wall behind a perfect record of their passage. But when we finally look, the wall tells a completely different story. It is a story that defies the logic we hold so dear. There are not two lines. Instead, there is a whole series of lines, an alternating pattern of light and dark bands spread across the wall. Many electrons have landed in the very center directly behind the solid barrier between the slits, a place that should have been impossible to reach. Other areas are completely untouched, even though they are directly behind the openings. This pattern is not the signature of particles. It is the unmistakable signature of waves. Imagine standing at the edge of a still pond and watching as waves ripple out from 2 points. Where the crest of one wave meets the crest of another, they combine, creating a larger wave. Where the crest of one wave meets the trough of another, they cancel each other out, leaving the water perfectly still. This is interference, and the pattern on our wall with its bright bands of many impacts and dark bands of no impacts is a perfect interference pattern. But how can this be? We sent the electrons one at a time. A single electron, a single particle, cannot interfere with anything, unless each electron somehow went through both slits at once. This is the central breathtaking mystery of the quantum world. The electron leaves its source as a particle. It arrives at the wall as a particle, making a single tiny dot. But in the journey between it, behaves as if it were a wave, a shimmering field of possibility that spreads out and explores all available paths simultaneously. It is like watching footprints appear on a misty beach. We see a single set of prints materialize in the sand at the water's edge, but we never see the walker. If we look back at the dunes from where the walker came, we see not one path, but a strange wave-like pattern of disturbed sand leading from 2 separate openings in a fence. It is as if a single person created a pattern that could only be made by 2 interfering with each other. This seemingly impossible idea was given a voice by a young French physicist named Louis de Broglie. He proposed something audacious, a statement of profound symmetry for the universe. If waves of light could sometimes behave like particles, the photons we met earlier, then perhaps all particles, everything with mass, could sometimes behave like a wave, an electron, a proton, an atom, even a grain of sand or a planet. Everything has a wave nature. The reason we don't see the world dissolving into a shimmering sea of waves is that for large objects, this wavelength is infinitesimally small. its effects completely negligible. But for the electron, its wave nature is not a footnote. It is the essence of its being. This wave is not a physical ripple in some cosmic ocean. It is a wave of probability. It is a mathematical description of potential. Before the electron hits the wall, it doesn't have a single definite location. It exists as this probability wave, a ghostly mist of what could be. This mist flows through both slits, and just like a water wave, it interferes with itself. It creates regions where the probability of finding the electron is high. These become the bright bands. And it creates regions where the probability is zero. These become the dark bands of nothingness. When the wave of potential touches the detector wall, the universe, in a sense, forces it to make a choice. The wave collapses. The mist of possibility condenses into a single droplet of reality, and one tiny dot appears on the screen. But the final location of that dot was guided invisibly by the ghost of the wave that came before it. Each solitary electron in its travels is guided by a map of probabilities that it creates for itself by interfering with its own potential paths. It is both particle and wave, a definite thing, guided by an indefinite ghost. This duality is not a trick, nor is it a failure of our instruments. It is the fundamental, irreducible nature of matter. Everything we have ever touched or seen is built from these strange entities that refuse to be one thing or the other. They are a constant dance between the definite and the potential, between being and becoming. This realization shatters the old solid world of simple objects and replaces it with a tapestry woven from threads of probability and potential. Having glimpsed this strange dual nature of reality's smallest actors, we are left to wonder, who are they? What is this fundamental cast of characters that dances this quantum waltz? We have spoken of the electron, this first and most famous member of the quantum realm. But it is not alone. It is part of a vast and intricate family. To truly understand the tapestry of existence, we must meet its threads. It is time to open the curtain and meet the two great families of particles that build everything we see and touch. To understand this new reality, we need a map. Not a map of paper and ink, but a map of understanding patiently assembled over a century of brilliant painstaking and often baffling work. This map is known as the Standard Model of Particle Physics. It is to date humanity's most successful and precise description of the fundamental constituents of the universe and the forces that govern them. It is not a final theory of everything, and its creators would be the first to admit its imperfections, its unanswered questions. But to look at it is to see a breathtaking architecture, an elegant and surprisingly simple blueprint for the cosmos. Imagine this map not as a chart, but as a grand family tree of reality itself. At the very top, there is a great divide, a fundamental schism that splits all of existence into two primary categories. On one side, you have the particles of substance. These are the bricks, the timber, the very stuff of which things are made. Physicists call them fermions. Every speck of dust, every drop of water, every living cell, you and I, we are all composed of these fermions. They are the tangible essence of the world. They have mass, they take up space, and they obey a deep and inviolable rule. No two identical fermions can ever occupy the exact same state at the exact same time. This principle of exclusion is what makes matter solid. It's the reason you don't fall through your chair, the reason the floor holds you up. It is the quiet, stubborn no that gives the universe its structure. On the other side of this great divide are the particles of interaction. These are the messengers, the carriers of force. The grammar that dictates how the particles of substance behave. Physicists call them bosons. They are not the bricks, but the mortar that holds the bricks together. They are not the actors on the stage, but the forces of love, conflict, and communication that pass between them. Gravity, light, electricity, the powerful glue that binds the heart of an atom, all of these are mediated by bosons. Unlike their fermion cousins, bosons are sociable. Many of them can pile into the very same state, creating powerful, coherent effects like the beam of a laser. For now, let us set aside the force-carrying bosons, the messengers, and turn our full attention to the particles of substance. Let us focus on the fermions, the building blocks of you, me, and everything we can see. Because here, within this great kingdom of matter, we find another profound division. It seems the universe, in its elegant simplicity, chose to build all of creation from just two core families, two ancient and distinct clans. The first of these families is called the quarks. The name itself is whimsical, pulled from a line in a James Joyce novel, a hint of the playful humility scientists felt as they uncovered a reality stranger than any fiction. The quarks are the intensely social, deeply communal family. Their defining characteristic is that they are never ever found alone in the wild. They are bound together by the strongest force known in nature, the strong nuclear force, a bond so powerful that to try and pull two quarks apart would require infinite energy. They exist only in tight-knit groups, forming composite particles. There are 6 types, or flavors, of quark, and they come in 3 generations, like sets of cousins, each generation heavier and more unstable than the last. The first generation contains the 2 most important, the up quark and the down quark. These are the bedrock of our world. Combine 2 ups and 1 down, and you build a proton. Combine 1 up and 2 downs, and you build a neutron. And with protons and neutrons, you can build the nucleus of every single atom in the periodic table. The other 4 quarks, the Yashcharm, Dyasha, and the strange, and the much heavier, top, and ear bottom, Gash, are more exotic. They existed in abundance in the hot, dense chaos of the early universe, but today they are fleeting visitors, created only in the collisions of high-energy particle accelerators, winking into existence for a fraction of a second before decaying back into their lighter, more stable relatives. They are echoes of a more violent cosmic past, but the story of stable matter, the story of us, is written almost entirely with ups and downs. This, then, is the first family, the quarks, the inseparable foundational clan that forms the dense, heavy core of every atom. The second family of matter particles is called the free leptons. Their name comes from the Greek word leptos, meaning slight or slender, because the first members of this family to be discovered were incredibly lightweight compared to the particles made of quarks. If the quarks are the communal family forever bound together, the leptons are the stark individualists. They do not feel the strong nuclear force that glues quarks together, and so they are free to wander the cosmos alone. You are already intimately familiar with the most famous member of the lepton family, the electron. This is the tiny, negatively charged particle that orbits the atomic nucleus. It is the electron's dance, its leaping between energy levels, its sharing and trading with other atoms, that gives rise to the entirety of chemistry. Every chemical bond, every biological process, every flash of lightning, and every spark of thought in your brain is governed by the behavior of this one fundamental lepton. Like the quarks, the leptons also come in 6 flavors arranged in 3 generations. Alongside the familiar electron, there are 2 heavier unstable cousins, the mon ds and the b tau ds. Both are like super-heavy electrons, and like the heavier quarks, they decay almost instantly. Each of these 3 charged leptons has a mysterious ghost-like partner, a neutrino. There is an electron neutrino, a muon neutrino, and a tau neutrino. These particles are almost massless. They have no electric charge. They interact so weakly with other matter that trillions of them produced by the sun are streaming through your body every single second without you ever feeling a thing. They are the universe's ultimate introverts, passing through planets and stars as if they were empty space. And that is the complete picture of matter, all of it. The staggering complexity of the world, the swirling galaxies and burning stars, the mountains and oceans, the intricate dance of life, is all built from the members of these 2 families, the quarks huddled together to form atomic nuclei, the leptons, like the electron, circling those nuclei to complete the atoms. This is the cast of characters, a world of just 2 families whose interactions governed by the bosons write the entire story of the cosmos. We have now sketched the outlines of our map. We see the great division between substance and force, and within substance, the 2 clans of quarks and leptons. While the quarks form the dense, hidden core of reality, it is the other family, the lighter, more elusive one, that we interact with most directly. They are the ones that carry electricity, that define the size and shape of atoms, that paint the world with light and shadow. To truly understand the atom, and thus ourselves, we must first get to know these solitary wanderers. Let us begin, then, with the leptons, the light ones. With our map of the Standard Model unfolded before us, we can now begin our quiet exploration. We will not start with the bustling, crowded continents of matter, but with the more solitary inhabitants of this quantum landscape. They are a family of particles known as the leptons, a name derived from the Greek word for light or slender, and it is a fitting description. Unlike their more complex relatives, the leptons are true loners. They feel the gentle pull of gravity, they interact through the weak nuclear force, and the charged among them respond to the familiar call of electromagnetism. But they remain aloof from the universe's most powerful binding agent, the strong nuclear force. They are the free spirits of the subatomic world, existing as distinct individual points of reality. Our journey begins with the most famous member of this family, the one you have known your entire life, the electron. If the atom is a miniature solar system, the electron is its tireless orbiting planet. It is the fundamental carrier of negative electric charge, a property as intrinsic to it as its own existence. It is the electron's constant dance that defines the world of chemistry. Every solid object you can touch, every scent you can smell, every color you see, all are the result of electrons being shared, exchanged, or excited. They are the artisans of the material world, tirelessly weaving the bonds between atoms to create molecules, the very fabric of our reality. Think of the humble glass of water on your table. It is nothing more than countless molecules of hydrogen and oxygen held together in an elegant embrace. That embrace is the work of electrons shared between the atoms in a covalent bond, a pact of stability that gives water its life-sustaining properties. The electricity that flows silently through the walls of your home is a river of these same electrons moving in a coordinated current. The light from your lamp is born when electrons leap from one energy level to another, within an atom releasing a photon, a tiny packet of light in the process. The electron is dependable, stable, and essential. It is the anchor of the lepton family, the particle that makes our world tangible, colorful, and alive. Without it, there would be no atoms as we know them, no chemistry, no life. It is the quiet, reliable foundation upon which complexity is built. But the electron is not alone. Like a firstborn child in a family of 3, it has 2 heavier, more enigmatic siblings, the muon and the tau. Imagine the electron as a perfectly formed tiny sphere of potential. Now imagine a second sphere, identical in every way. Same negative charge. Same fundamental loneliness, but over 200 times more massive. This is the muon. It is a heavier echo of the electron, a fleeting visitor to our world. Muons are not typically found in ordinary matter because they are unstable. They are born in high-energy collisions, such as when cosmic rays, particles from deep space, strike our upper atmosphere. They rain down upon us constantly invisible and harmless, passing through our bodies by the dozen every minute. But their existence is breathtakingly brief. In just over 2/millionths of a second, a muon decays, transforming into an electron, a nearly massless wisp called a neutrino, and its antimatter counterpart. It is a ghost of a particle, a heavier thought that cannot hold its form for long. And then there is the third sibling, the tau lepton. If the muon is a heavier echo, the tau is a resounding boom. It is nearly 17 times more massive than the muon, and over 3,500 times more massive than the electron. The tau is the titan of the charged leptons, a particle of immense weight, and with great mass comes great instability. Its life is almost unthinkably short, lasting for less than a trillionth of a second before it too decays into other lighter particles. It is found only in the most violent corners of the universe, in the heart of powerful particle accelerators, or perhaps in the aftermath of a supernova. The electron, the muon, the tau, 3 generations of the same idea, each with more mass and each more fleeting than the last. It is a profound and unanswered question in physics why nature decided to repeat this pattern 3 times. Why 3 generations? Why this particular hierarchy of mass? The Standard Model describes it perfectly, but it does not explain the why. It simply presents us with this elegant, mysterious family portrait. Each of these 3 charged particles has a partner, a companion, that completes the family structure. These are the famous and famously elusive neutrinos. For every charged lepton electron, muon and tau, there is a corresponding neutral lepton, the electron neutrino, the muon neutrino, and the tau neutrino. They are the ghosts of the Standard Model. They have no electric charge, which means they are completely invisible to the electromagnetic force. They do not feel the strong force. They only interact through the weak force and gravity, both of which are exceptionally feeble. As a result, neutrinos can travel through almost anything as if it were not there. Trillions of neutrinos, born in the fiery heart of our sun, are streaming through your body, right now passing through every atom of you, through the chair you sit on, and through the entire planet Earth, emerging on the other side without leaving a trace. To a neutrino, a light year of solid lead would be mostly empty space. For decades they were thought to have no mass at all. We now know they have a tiny, almost infinitesimal mass, but we still don't know what it is. Their ghostly nature is compounded by one of the strangest phenomena in all of quantum mechanics, neutrino oscillation. As they travel through space, these neutrinos can spontaneously change their identity. An electron neutrino can become a muon neutrino, which can then become a tau neutrino, and back again. They are cosmic shapeshifters, constantly morphing from one form to another on their lonely journey across the cosmos. They are whispers of a reality so subtle it barely registers with our own carrying secrets from the hearts of stars and the very first moments of the universe. So this is the lepton family in its entirety, 6 particles. 3 carry an electric charge and form the basis of so much of what we see and touch. And 3 are their neutral ghostly partners drifting through the universe like secrets. They are all fundamental indivisible points. As far as we know, you cannot break a lepton apart. They are the final irreducible layer of this part of reality. Yet, as vital as they are, these 6 leptons cannot build the world alone. They are the artists who paint the details, the messengers who carry electricity and energy. They orbit and interact, but they do not form the dense, resilient core of things. The electron circles the atomic nucleus, but what is that nucleus made of? What holds it together against the incredible repulsive force of its own positive charge? For that, we must leave the realm of the solitary leptons and turn to an entirely different family of particles. We must venture into the tightly bound, hidden world of the quarks. They are the true builders of substance, a family that exists only in inseparable groups, governed by a force so powerful and strange it has been given the name of color. They are the heart of matter itself, and it is to their story we now turn. Having acquainted ourselves with the solitary leptons, those wanderers of the quantum landscape, we now turn our attention to a profoundly different kind of particle. If the leptons are the hermits of the cosmos, then what we are about to discover are the members of an inseparable foundational community. We move from the outer orbits of the atom, past the electron's ephemeral cloud, and journey deeper still into the very heart of the nucleus, where protons and neutrons are clustered together. For decades, these 2 particles were thought to be fundamental, indivisible points of substance. But as we look closer with the quiet focus of our inner mind, we see that they too are composite. They are small, self-contained universes, and within them reside the most reclusive and social particles known to existence, the quarks. The name itself, quark, was plucked from a line in James Joyce's dense and playful novel, Finnegan's Wake. 3 quarks for muster mark. It was a fittingly strange name for a truly strange idea. The theory proposed in the 1960s was that the protons and neutrons that give atoms their weight and identity were not elementary at all. They were, in fact, vessels each containing a trio of these more fundamental entities. This was a radical shift in perspective. It was like discovering that the bricks used to build a great cathedral were themselves made of 3 smaller, intricately bound pebbles. These pebbles, the quarks, are the true bedrock of the material world. Just as the leptons come in a family of 6, so do the quarks. They are organized into 3 generations or pairs, each heavier and more unstable than the last. The first generation contains the 2 most famous and most essential, the up quark and the down quark. These 2 are the workhorses of the universe, An ordinary proton is a tiny stable society of two up quarks and one down quark. A neutron, its near twin, is composed of one up quark and two down quarks. Every atom in your body, every star in the night sky, every grain of sand on the shore is constructed from a near infinite combination of just these three particles, electrons, up quarks and down quarks. It is an astonishing testament to cosmic simplicity. The other four quarks are more exotic. The second generation gives us the charm quark and the strange quark. The third and heaviest generation contains the top quark and the bottom quark. These heavier quarks are like fleeting thoughts in the mind of the cosmos. They are produced in high-energy collisions in particle accelerators or in the hearts of exploding stars, but their existence is breathtakingly brief. They live for a tiny fraction of a second before decaying into their lighter, more stable cousins, the up and down quarks. They are crucial for our understanding of the complete model of reality, but they are not part of the enduring substance of our world. They are the beautiful ephemeral blossoms on the sturdy ancient tree of matter. But this discovery posed a profound puzzle. A proton contains two up quarks each, carrying a positive electric charge. The nucleus of an atom, in turn, is a dense collection of protons, all positively charged. From our understanding of electricity, these particles should repel each other with ferocious intensity. The nucleus of an atom ought to fly apart in an instant. Yet it doesn't. The very existence of atoms more complex than hydrogen tells us that there must be another force at play, a force so powerful it can overwhelm the mutual repulsion of protons, binding them together. This is the strong nuclear force, and its origin lies in a property unique to quarks, a property given another wonderfully whimsical name, color. This color charge has absolutely nothing to do with the colors we see with our eyes. It is simply a label for a new kind of charge, just as positive and negative are labels for electric charge. Quarks come in one of three colors, red, green, or blue, and for every quark there is an antiquark with an anticolor, anti-red, anti-green, or anti-blue. And the unbreakable rule of the strong force, the law that shapes all matter, is this: quarks can only exist in combinations that are color neutral. They are compulsively social and must form groups where their colors cancel out, creating a combination that appears white. This is the principle of quark confinement, and it explains why we have never ever seen a single quark in isolation. They are prisoners of their own society. There are two ways they can achieve this color neutrality. The first is to form a group of three, a baryon. A proton, for example, is made of three quarks, one red, one green, and one blue. Just like combining the primary colors of light, this trio results in a color neutral or white particle. This is the stable family unit of the quantum world. The second way is to form a pair consisting of one quark and one antiquark. For example, a red quark might pair with an anti-red antiquark. The color and anticolor neutralize each other, forming a short-lived particle called a meson. These are far less stable than the baryons' fleeting partnerships that quickly decay. The force that holds these quarks together is unlike any other force we know. Imagine two quarks connected by an invisible cosmic rubber band. If they are close together, the band is loose and they can move around with relative freedom inside their proton or neutron home. But if you try to pull them apart, the band stretches and the force pulling them back together grows stronger. It doesn't weaken with distance, it increases. If you pour in enough energy to stretch the band to its breaking point, something extraordinary happens. The band doesn't just snap. The energy you've added to the system is so immense that it converts into matter, following Einstein's famous equation E/mc2. A new quark and antiquark pair springs into existence from the vacuum, one latching onto the quark you were trying to free, the other joining the one left behind. You began with one particle, and in your attempt to isolate a single quark, you have ended up with two. You can never win. You can never pull a single quark free. They are bound together for eternity. So we find that the very foundation of matter is governed by a kind of hidden collaboration. The substance of the world is not built from solitary bricks, but from inseparable triplets and fleeting pairs, all held together by a force born of a property we call color. We have explored their flavors, their generations, and the strange, beautiful rule of confinement that dictates their existence. We see now that the particles of the Standard Model are not just a random collection of points, but a cast of characters with distinct personalities and strict social rules. Yet there is another property, a deeper rule of order, that governs them all. It is a feature shared by quarks and leptons alike, an intrinsic characteristic, as fundamental as charge or mass. It is a kind of constant internal motion, a quantum hum, that dictates how these particles can arrange themselves in space, how they build atoms, and why the universe doesn't collapse into an infinitely dense point. To understand this, we must now turn our attention to the subtle and profound quantum rule of spin. As we delve deeper into the subatomic realm, into the very heart of what constitutes reality, we find that the particles we have met, electrons, quarks, neutrinos, are not merely defined by their mass or their charge. They carry with them another property, one far more subtle, and in many ways far more profound. It is a quality that doesn't shout its presence, but whispers a fundamental law that shapes the entire cosmos. This property is known as spin. Now the word spin conjures a familiar image, a spinning top, a rotating planet, a dancer in a graceful pirouette. And while this gives us a starting point, a hook for our intuition, we must be gentle with the analogy. A quantum particle is not a tiny marble spinning on its axis. Its spin is an intrinsic, unchangeable characteristic as fundamental to its identity as its charge. You cannot make an electron spin faster or slower, nor can you stop it from spinning altogether. It simply has spin, just as it has mass. It is a built-in quantized form of angular momentum, a secret rotational value that it carries everywhere it goes. For a particle, like an electron, this value is always the same magnitude, but it can point in one of two directions, which we label for convenience as up or down. Think of it not as a direction in physical space, but as an internal state of being a binary choice that the particle has made. This seemingly simple twofold property is the source of magnetism in many materials. Each particle with spin acts like a minuscule compass needle, and when countless needles align, a powerful macroscopic force emerges. But its most important role is not to create magnets. It is to serve as a cosmic administrator, enforcing a rule of profound elegance and consequence. This rule partitions the entire particle zoo into two great families. On one side, we have the particles of matter, like the electrons and quarks that build our world. They have spins that come in half-integer values, 1/2, 3/2, and so on. These are the fermions, named after the physicist Enrico Fermi. On the other side are particles with whole integer spins, 0, 1, 2. These are the bosons, named after Satyendra Nath Bose. For now, let us focus on the fermions, for they are the architects of structure, and the rule they obey is what prevents the universe from collapsing into an indistinct soup. Imagine the universe as a grand silent ballroom. The fermions are the dancers, each one moving to an unheard rhythm. And in this ballroom there is one unbreakable rule, a law so fundamental it is woven into the fabric of space-time itself. This is the Pauli exclusion principle. It states with absolute authority that no two identical fermions can ever occupy the exact same quantum state at the same time. What does this mean for our dancers? It means each one must be unique. No two dancers can stand on the very same spot, with the very same energy, moving in the very same way, and holding the very same posture, the same spin orientation. If one electron in an atom is in a particular energy level, with its spin pointing up, no other electron can join it in that exact configuration. Another electron can occupy the same energy level, but only if its spin points down. They must differ in at least one defining characteristic. The cosmic dance floor demands individuality. This single simple prohibition is the reason matter exists as we know it. Consider an atom. Without the exclusion principle, all of its electrons, seeking the lowest possible energy state, would cascade downwards and pile on top of each other in the innermost shell, right next to the nucleus. Atoms would be tiny, dense, and chemically inert. There would be no structure, no variety, no life. But the rule forbids this. It orchestrates the building of the atom with meticulous care. The first energy level, the shell closest to the nucleus, can only accommodate two electrons, one spin up, one spin down. Once that shell is full, the ballroom's rule dictates that the next electron must find a different state. It is forced to occupy a higher energy level, a shell further out from the nucleus. This process continues shell by shell, with each new electron forced to find its own unique quantum address. This is the origin of the periodic table of elements. The elegant repeating patterns of chemical properties that we see, the reactivity of sodium, the nobility of neon, the life-giving versatility of carbon, are all direct consequences of this quantum rule of exclusion. The way atoms bond to form molecules, the very foundation of chemistry and biology, is a testament to this dance. It is the reason that you can rest your hand on a solid table and not pass straight through it. The fermions in your hand and the fermions in the table are all obeying this deep law, refusing to occupy the same space in the same way. The solidity we experience is not a property of impenetrable little spheres, but the result of a silent universal agreement among particles to maintain their distance to respect each other's state of being. This principle gives the universe its texture, its complexity, and its stability. From a simple no, nature builds everything. From a prohibition comes possibility. From a rule of exclusion comes the rich and intricate structure of the cosmos. The fermions, the solitary dancers, create the enduring architecture of reality because they are not allowed to lose their individuality in a crowd. And so, we see the world of matter built from these fermions, governed by this strict choreography. But this raises a profound question. If the particles of matter are so insistent on keeping to their own unique states, what is it that binds them together at all? What holds the electrons in their orbits around a nucleus? What overcomes the immense electrical repulsion between protons to clamp them together in that same nucleus? A dance requires more than just dancers and rules. It requires a connection, a force, an interaction that passes between them. The dancers, for all their individuality, are not alone. They are constantly communicating, influencing one another across the empty spaces of the atom. This communication is not carried out by the fermions themselves. It is the work of the other family of particles, the bosons. Unlike the solitary fermions, bosons are profoundly social. They do not obey the exclusion principle. In fact, they prefer to be in the same state, to pile on top of one another, to act in perfect unison. They are the messengers, the carriers of information, the mediators of the fundamental forces of nature. To understand how the world is held together, we must now turn our attention from the dancers to the messages they pass between them, to the very nature of the forces that make the cosmic dance possible. And so, we arrive at this new understanding that a particle, like an electron or a quark, is not just a point of mass and charge, but a holder of intrinsic spin, a secret angular momentum that governs how it arranges itself in the cosmos. But properties like spin and charge are not merely passive labels. They are invitations. They are the very means by which particles engage with one another, the handles through which they feel the pull and push of the universe. They are what allow particles to participate in the grand conversation of existence, a conversation conducted not through words, but through forces. For centuries we imagined forces as mysterious, invisible tendrils reaching across empty space. Newton spoke of gravity as an instantaneous action at a distance, a concept that even he found philosophically unsettling. How could the sun, millions of miles away, possibly tell the earth to orbit it? How does one magnet know to repel another without anything visibly passing between them? The quantum world offers a profoundly beautiful and revolutionary answer. It tells us that nothing acts at a distance. For every action there is a messenger. For every force there is an exchange. Imagine a vast, perfectly smooth sheet of ice under a winter sky. Upon it, two skaters stand motionless, facing each other a short distance apart. There is no wind, no slope, no friction. They are perfectly isolated. Now one skater holds a heavy ball. She throws it to her partner. In the moment she pushes the ball forward, the law of conservation of momentum demands that she herself is pushed backward. Her skates glide silently in the opposite direction. A moment later, her partner catches the ball. The impact of the catch imparts momentum to him, and he too begins to slide backward away from the first skater. Let us pause and observe what has just happened. Two skaters who never touched each other have moved apart. An invisible repulsive force seems to have acted between them. But we know the secret. The force was not some magical influence. It was the result of a physical object being exchanged between them. The ball was the messenger of that force. This simple analogy is our first glimpse into the modern understanding of all fundamental forces. In the quantum realm, when two electrons repel each other, it is not because of an abstract field of negative charge. It is because they are constantly exchanging messenger particles. They are playing a perpetual game of catch on the fabric of space-time. The particles that make up matter, the electrons, the quarks, the neutrinos, which are collectively known as fermions, are the skaters. The messenger particles they exchange, the carriers of the forces, are a different class of particle entirely. They are known as bosons. This idea transforms our picture of empty space. The vacuum is not truly empty. It is a shimmering, seething cauldron of potential, a stage for a constant frantic exchange of these force-carrying bosons. But there is a subtlety here. The messengers in our ice rink analogy, the heavy ball, was a real tangible object. The bosons exchanged between particles are often of a more elusive kind. They are called virtual particles. A virtual particle is a phantom. It is a particle that flashes into existence, for an immeasurably short period travels between two interacting particles, delivers its message of force, and then vanishes. It exists on borrowed time and borrowed energy, alone granted by one of the most curious principles of quantum mechanics, the Heisenberg uncertainty principle. This principle states that you cannot know both the precise energy of a system and the precise time for which it has that energy. This allows for tiny fleeting fluctuations in energy, just enough for a virtual particle to be created from nothing, deliver its push or pull, and disappear before the universe at large can register its violation of energy conservation. They are the whispers in the cosmic conversation, never fully spoken aloud, but their meaning is perfectly understood by those who hear them. The force is real, even if the messenger is virtual. This concept of forces as an exchange of particles is a monumental leap, but quantum field theory invites us to take one step further to a viewpoint that is perhaps the most profound in all of modern physics. It asks us to stop thinking of particles as primary. It asks us to imagine that the most fundamental reality is not the particle, but the field Cassie. Think of the entire universe as a silent, invisible ocean. This ocean is not made of water, but of something far more fundamental. In fact, there is not just one ocean, but many, all interpenetrating, all filling every corner of space and time. There is an electron field. There is a quark field, and so on for every fundamental particle. In this view, a particle, what we think of as a tiny solid dot, is nothing more than a localized vibration, a ripple, a tiny persistent excitation in its corresponding field. An electron is just a knot of energy vibrating in the electron field. When you see light, you are seeing ripples in the electromagnetic field. From this perspective, the interaction between two particles becomes even more elegant. Imagine two ripples in the electron field, two electrons. As they approach each other, their presence disturbs the fields around them. Specifically, they cause a secondary ripple to form in another field, the electromagnetic field. This new ripple travels from one electron ripple to the other, transferring energy and momentum. This secondary ripple is the virtual photon, the messenger of the electromagnetic force. The conversation of the universe is not between skaters, but between waves. A vibration in one field creates a vibration in another, which in turn influences the first. It is a world of interconnected resonances, a cosmic tapestry woven not from discrete threads, but from the continuous shimmering fabric of the fields themselves. The push and pull of the cosmos is the music played upon these fields, a symphony where matter particles are the sustained notes, and force particles are the fleeting harmonies that connect them. We have journeyed from a simple picture of skaters on ice to a vision of reality as a set of infinite vibrating fields. We now understand the mechanism forces our exchanges, conversations carried by messenger particles, the bosons. These messages can be fleeting and virtual, but their impact shapes everything from the structure of an atom to the burning of a star. With this new lens, we are ready to examine these cosmic conversations one by one. We can now begin to listen in, to learn the language of each fundamental force. It is only fitting that we start with the force that is most familiar to us, the one responsible for light, for electricity, for chemistry, and for the very structure of the world we see. Let us turn our attention to the first and most famous of these messengers, the photon, and explore the infinite brilliant reach of the electromagnetic force. Talk to one another to build and to shape the fabric of reality. And of all the conversations happening in the universe, the most common, the most luminous, is the one spoken in the language of light. This conversation is carried by a single, tireless messenger, the photon. It is the quantum of the electromagnetic field, the force that binds atoms, paints the world with color, and carries the warmth of a distant star across the silent void. To understand this force is to understand the architecture of our entire world, from the chair you sit on to the thought flickering through your mind. And the best way to understand it is to follow one of its messengers on its ancient and epic journey. Our story begins in a place of unimaginable violence and creation, the core of our sun. Here the pressure is over 200 billion times that of Earth's atmosphere, and the temperature soars to 15 million degrees. It is not a place of fire, but of pure, seething plasma, a churning soup of atomic nuclei and free electrons stripped from their atomic homes by the sheer energy of it all. In this cauldron, the universe's simplest elements, hydrogen nuclei, are crushed together. They overcome their natural repulsion in a process of fusion, forging helium and releasing a titanic burst of energy. In one such infinitesimally small, yet cosmically significant act of creation, our photon is born. It springs into existence not as a particle of matter, but as a pure packet of energy, a ripple in the electromagnetic field. It carries no mass, no charge, only a specific wavelength and an unyielding momentum. And from the moment of its birth, it moves at the only speed it can, the speed of light. But its path is not a simple one. The sun's interior is opaque, a dense fog of charged particles. Our photon travels for a mere fraction of a second before it collides with an electron, which absorbs it completely. For a fleeting moment, the photon ceases to exist, its energy transferred to the electron, which jumps to a higher state. But this state is unstable. Almost instantly the electron relaxes, releasing the energy by emitting a new photon. This new photon is not the same one, but it carries the same legacy of energy. It shoots off in a completely random new direction, only to be absorbed and re-emitted again and again and again. This is the photon's million-year journey to the sun's surface. It is a staggering, drunken walk. A single step takes an eternity in particle terms, but covers less than a centimeter. For thousands, even hundreds of thousands of years, our photon's ancestor energy is trapped in this chaotic dance, a cosmic pinball ricocheting through the solar plasma. Yet with every exchange it is participating in the fundamental act of electromagnetism, the interaction between light and charge. This is the force in action, a constant give and take that churns the heart of a star. Slowly, painstakingly, the energy works its way outward. As it moves into cooler, less dense layers of the sun, the journey becomes a little easier. Finally, after a pilgrimage lasting longer than all of human civilization, the energy now embodied in our final photon reaches the sun's visible surface, the photosphere. Here, for the first time, the path ahead is clear. There are no more charged particles to block its way. With nothing to stop it, our photon is launched into the cold, silent vacuum of space. Its journey is now pure and direct. Behind it, the churning star. Ahead, the vast, dark tapestry of the cosmos. For 8.5 minutes, it crosses the 150 million kilometers to Earth, a tiny, perfect messenger on an unwavering trajectory. As it travels, it is the embodiment of a profound physical truth, one discovered by James Clerk Maxwell in the 19th century. He realized that electricity and magnetism were not separate phenomena, but two sides of the same coin. A moving electric charge creates a magnetic field, and a changing magnetic field creates an electric one. They generate each other, a self-propagating wave of energy that needs no medium to travel. This wave is light. Our photon is the smallest possible amount of that light, the quantum of that unified electromagnetic field. Its range is in principle infinite. Because the photon has no mass, it can travel forever without its message fading, merely spreading out and becoming fainter with distance. Every photon ever emitted from the first stars, after the Big Bang, is theoretically still traveling, carrying a postcard from a time long past. Our photon's journey is nearing its end. It streaks through Earth's upper atmosphere, dodges dust motes and water vapor, and on a clear day finishes its journey by passing through the lens of a human eye. It comes to a stop on the retina, striking a single molecule of rhodopsin within a photoreceptor cell. In that final definitive act, the photon is absorbed. Its long journey is over. Its energy born in the heart of a star hundreds of thousands of years ago is transferred to this delicate biological machine. The energy kicks off a chemical reaction. The rhodopsin molecule changes shape, triggering a cascade that sends a tiny electrical signal down the optic nerve and into the brain. There, this signal is woven together with millions of others interpreted and rendered into the subjective experience of sight. The perception of the color blue, the glint of sunlight on water, the face of a loved one, all are the final chapter in the story of countless photons, each having completed a similar cosmic journey. And this force, this exchange of light, governs nearly everything we perceive. It is the electromagnetic force that holds the electron in its orbital dance around the atomic nucleus, giving the atom its size and structure. It is the force that dictates all of chemistry, forging the bonds between atoms to create the molecules of air, of water, of life itself. The firmness of the ground beneath your feet is the electromagnetic repulsion between the electrons in your shoes and the electrons in the floor. The sound of a voice is a vibration traveling through air molecules held together by this same force. It is the architect of the world at our scale, the universal glue of our everyday experience. It holds the atom together, a delicate balance between the negatively charged electrons and the positively charged nucleus at the center. The attraction is perfect, elegant, and explains so much of our world. But it also presents us with a profound and troubling paradox. If we look closer into that tiny, dense nucleus, we see that it is composed of protons, each carrying a positive charge. And electromagnetism is clear, like charges repel. The repulsion between those protons, crammed into such an impossibly small space, should be gargantuan. The nucleus could not possibly hold itself together. It should instantly fly apart in a burst of energy. And yet it doesn't. The atoms that make up our world are stable. The universe exists. This implies that within the heart of the atom, another force must be at work. a force so powerful it can overwhelm the immense repulsion of electromagnetism, binding the nucleus together against all odds. It is a force we never feel directly, for its reach is infinitesimally small, but without it, nothing, not a single atom, not a single star, not a single one of us could exist. From the vast open conversation of light, we now turn inward to a dialogue spoken in a space so small it defies imagination. The photon messenger of the electromagnetic force can cross the entire cosmos, carrying its message from a galaxy's edge to the pupil of an eye. But the universe is built on more than just long-distance calls. It is also founded on an intimate, unbreakable promise, a force of such incredible strength that it operates only within the heart of the atom itself. It is a bond that holds the very world together, a power that works in silent, absolute opposition to the electric repulsion we just explored. Consider the nucleus of an atom, any atom that makes up you, the air you breathe, the ground beneath your feet. A helium atom, for instance, has 2 protons huddled together in its core. Each proton carries a positive charge, and as we know, like charges repel. They want to fly apart with a force that at this microscopic distance is colossal. If electromagnetism were the only story being told in the nucleus, no element heavier than hydrogen could ever exist. Every atom would instantly tear itself apart in a blaze of mutual repulsion. The universe would be nothing but a thin, formless gas of lonely protons and electrons. And yet, here we are. The mountains stand, the oceans churn, the stars burn for billions of years. Something is holding it all together. Something is winning the fight against the infinite reach of electromagnetism. This victor is the strong nuclear force. It is the most powerful of the 4 fundamental forces, over 100 times stronger than electromagnetism. And it is the reason that matter, as we know it, is stable. To understand this force, we must journey deeper than ever before, past the electron shells, past the boundary of the nucleus, and into the very fabric of the protons and neutrons themselves. For a long time, we thought these particles were fundamental, the final indivisible building blocks. But the quantum world is a place of nested secrets. Protons and neutrons are not solitary entities. They are composite particles, each a tiny, bustling community of 3 even smaller particles called quarks. And it is here, in the space between the quarks, that the strong force reveals its true nature. Its messenger is not the photon, but a particle aptly named the gluon. The word itself comes from glue, and there is no better description. Gluons are the quantum expression of a perfect, unbreakable adhesive. They flow between the quarks, binding them together in a ceaseless dynamic dance. Unlike the electromagnetic force, which has one type of charge, positive or negative, the strong force has a more complex kind of charge, which physicists whimsically named color. This has nothing to do with the colors we see. It is simply a label for 3 different types of strong force charge: red, green, and blue. Just as positive and negative electrical charges attract, these color charges interact in a specific way. A proton or neutron is always color neutral, containing one of each of the 3 quark colors which, like mixing primary colors of light, combine to make white. The gluons themselves carry color charge, which makes their behavior utterly unique. A photon, being electrically neutral, does not interact with other photons, but a gluon carrying color charge can and does interact with other gluons. This makes the field of the strong force a vibrant, self-interacting, and incredibly complex domain. It's not a simple line of force from one particle to another. It is a thick, sticky web of energy connecting the quarks. This leads to the most astonishing property of the strong force confinement. Imagine two quarks inside a proton connected by the gluon field. If you were to try and pull them apart, the energy required would be immense. The further apart you pulled them, the stronger the force between them would become, as if you were stretching a cosmic rubber band. The energy in the gluon field between them would increase and increase until eventually something remarkable happens. The band does not snap. Instead, the energy becomes so great that it converts into matter, following Einstein's famous equation E=mc2. A new quark and antiquark pair would spring into existence from the field itself, instantly bonding with the ones you were trying to separate. You would not end up with two isolated quarks. You would end up with two new pairs of bound quarks. This is why we have never seen a single free quark in nature. They are eternally confined within their family groups, inside protons and neutrons. The strong force is a perfect prison, a bond that cannot be broken. It ensures that the universe is made of stable composite particles, not a wild soup of fundamental quarks. So this is the force that glues quarks together. But how does this explain the stability of the entire nucleus? How does it bind a proton to a neutron, or two protons to each other? The answer lies in what is called the residual strong force. The intense interactions happening inside the protons and neutrons are so powerful that a small portion of their influence leaks out, like the muffled sound of a powerful engine heard through a thick wall. This residual force is what a nearby proton or neutron feels. It is much, much weaker than the primary force binding the quarks inside, but it is still more than strong enough to overwhelm the electromagnetic repulsion between protons at the tiny distances within a nucleus. It is this leakage, this sticky residue of the most powerful force in nature that holds the atomic nucleus together. It is the reason we have carbon and oxygen and iron. It is the reason we have the periodic table of elements, the foundation of all chemistry and biology. Every solid object, every complex structure in the cosmos owes its existence to this powerful but short-range conversation between the particles in its core. It builds the bricks of the universe, and it builds them to last. The strong force is the force of stability, of permanence of structure. It takes the fundamental chaos of the quantum realm and forges it into the reliable building blocks of reality. It is the universe's commitment to being, to creating things that endure. But existence is not only about endurance. It is also about change, about transformation. A star shines not just because its atoms are stable, but because under immense pressure they can become something new. The universe is not a static sculpture. It is a dynamic, evolving tapestry. And for that, for the engine of change, we must turn to a force that is far more subtle, a force that works not by binding, but by allowing one thing to become another. We must look to the quiet architect of transformation, the weak nuclear force, and of unimaginable strength a glue that holds the very essence of matter in a tight, unyielding embrace. It is a force of permanence, of stability. But the universe is not a static sculpture. It is a dynamic, evolving story. For a story to unfold, there must be change. For stars to be born, for elements to be forged, for life to even be possible, something must be capable of rewriting the rules of transforming one character into another. If the strong force is the force of being, there must also be a force of becoming. This is the story of the quietest, most subtle, and perhaps most profound interaction of all the weak nuclear force. It does not shout its presence across galaxies like light, nor does it bind with the indomitable grip of the strong force. The weak force is a whisper, an interaction so fleeting and intimate it happens on a scale almost too small to comprehend. Its messengers, the particles that carry its influence, are unlike any we have met before. They are not massless travelers like the photon or the gluon. They are titans heavyweights of the particle world known as the W and Z bosons. They are so massive, in fact, that their very existence is a frantic borrowed flicker. Born from the quantum foam, they live for less than a trillionth of a second before decaying. Their immense mass means their reach is tragically short, confined to a space far smaller than a single proton. The weak force is not weak because its punch is gentle. It is weak because its arms are short. It is a force of proximity, a secret past in the densest crowd, an interaction that changes everything it touches, but can only touch what is infinitesimally close. And what is the secret it whispers? It is the secret of identity. The weak force is the only force in nature that can change the very essence of a particle. What physicists call its flavor. Imagine a quark, a fundamental building block of a proton or a neutron. It can be an up quark or a down quark, two distinct identities. The strong force and electromagnetism can push them, pull them, and bind them, but they cannot change what they are. They can rearrange the letters, but they cannot change the letters themselves. The weak force, however, is a master of subatomic alchemy. In its fleeting, powerful embrace, it can coax a down quark to become an up quark, or an up quark to become a down. This single astonishing capability is the engine of the cosmos. When a down quark flips to an up quark, a neutron made of one up and two down quarks transforms into a proton made of two up and one down quark. This is not just a minor adjustment. It is a fundamental shift in the character of matter, and it is the key that unlocks the energy of the stars. Let us journey to a place where this quiet force becomes the protagonist in the grandest of cosmic dramas, the core of our Sun. Here the pressure is over 200 billion times that of Earth's atmosphere, and the temperature is a staggering 15 million degrees Celsius. It is a furnace of pure plasma where atoms are stripped bare and protons, the nuclei of hydrogen, whiz about in a frantic superheated dance. These protons are the sun's fuel. The goal is fusion to slam them together and forge heavier elements, releasing tremendous energy in the process. But there is a problem. Every proton carries a positive electric charge. As two protons approach each other, the electromagnetic force, that powerful force of repulsion between like charges, screams at them to stay apart. The sheer heat and pressure of the sun's core can force them to get incredibly close, but electromagnetism builds an almost impenetrable wall between them. Even if they could touch two protons, cannot form a stable nucleus on their own. The strong force, for all its power, needs a partnership between a proton and a neutron to truly take hold and begin building a stable atomic family. The sun would be a dark, cold ball of hydrogen, a failed star were it not for the whisper of the weak force. In this inferno, as two protons are momentarily crushed together against their will, the weak force intervenes. In a singular, miraculous instant, It reaches into one of the protons and flips an up quark into a down quark. The proton is no more. In its place is a neutron. As this transformation happens, two other tiny particles are born and flung away: a positron, the antimatter twin of an electron, and a ghostly neutrino. With this act of alchemy, the entire dynamic changes. The electromagnetic barrier is overcome. We now have a proton and a neutron, the perfect partners. The strong nuclear force, waiting in the wings, can finally leap into action, binding them together into a stable nucleus of deuterium or heavy hydrogen. The first crucial step in the Sun's fusion chain has been taken. From this single transformative event, the path is cleared for creating helium and releasing the light and heat that bathes our planet, the energy that fuels every leaf, every breath. The weak force, then, is the Sun's heartbeat. It is the gatekeeper of solar fusion. Its inherent weakness is actually a cosmic blessing. If it were stronger, the hydrogen fuel in the Sun's core would have burned out billions of years ago, long before complex life could ever have a chance to evolve on a rocky planet orbiting nearby. Its subtle, reluctant nature sets the pace for the universe. It is the slow, steady clockwork that allows stars to shine for eons, patiently forging the elements that would one day become planets, oceans, and us. But creation is only one side of its personality. The same mechanism that allows a proton to become a neutron also allows for the reverse. In an atomic nucleus, with too many neutrons for its own stability, the weak force can step in and change a neutron back into a proton, spitting out an electron in a process we call radioactive decay. This is the force that makes certain elements unstable, their nuclei slowly transforming over vast timescales. It is this predictable, steady decay that allows us to date ancient artifacts with carbon-14 to peer back into the history of our world. The weak force is both the midwife at the birth of starlight and the gentle hand that guides the transformation of matter through time. It is the ultimate engine of change. So we have now met three of the fundamental forces that govern our universe. We have seen the unbreakable grip of the strong force locking the heart of matter together. We have witnessed the far-reaching conversation of the electromagnetic force painting the cosmos with light and chemistry. And now we have uncovered the subtle, transformative whisper of the weak force, the agent of change that allows stars to shine and matter to become. Together they form a remarkably complete and elegant picture, a family of interactions described with breathtaking precision by the standard model of particle physics. They operate through the exchange of messenger particles, each with its own character, each playing its essential role in the quantum tapestry. And yet, as we stand back to admire this magnificent portrait of reality, we cannot help but notice that someone is missing from the family photo. There is another force, one we have known our entire lives. It is the first force we ever feel, the one that holds us to the earth and wheels the galaxies in their silent cosmic dance. It is a force that shapes the entire universe on the largest of scales, and yet, when we look for it here in the neat and tidy world of quantum mechanics, it is nowhere to be found. It stands apart, a gentle giant whose secrets we are only just beginning to unravel. We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense unyielding grip of the strong force, the powerful warden that locks quarks together inside protons and neutrons. And we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change. These three forces, with their corresponding particles, form a tidy, coherent family. They live within the same house, speak the same language of probabilities and fields, and obey the same quantum rules. But there is another presence in the universe, a force so familiar we feel it in our bones with every step we take, yet so alien to the quantum family that it remains an outsider, looking in from a distance. It is the oldest, most patient, and most far-reaching force of all. We can think of it as a gentle giant, whose footsteps are the orbits of planets, and whose breath is the slow, graceful dance of galaxies. This giant is gravity, and it is, for all our understanding, the profound problem at the heart of physics. Unlike the other forces, gravity does not seem to operate through the frantic exchange of messenger particles in the quantum foam. It speaks a different language entirely. To understand it, we must leave the bustling quantum city for a moment and step into the silent, sweeping cosmos as imagined by Albert Einstein. In his theory of general relativity, gravity is not a force in the traditional sense at all. It is a property of the universe itself. It is the shape of space and time. Imagine a vast, flat sheet of fabric, stretched taut and infinite. This is space-time, the stage upon which all of reality plays out. Now place a heavy ball in the center of this sheet. The fabric curves, sinking down around the weight. This curvature is what we experience as gravity. A smaller marble rolled nearby doesn't fall toward the heavy ball because of some mysterious pull. It simply follows the straightest possible path along the curved surface. The Earth is not pulled by the Sun. Rather, the Earth is freely moving through space-time that has been warped by the Sun's immense mass. Planets orbit, apples fall, and light itself bends as it passes a star, all because they are following the contours, the valleys and hills in the geometry of reality. It is a theory of breathtaking elegance and precision. It describes the cosmic ballet of celestial bodies with near-perfect accuracy. It is a world of smooth curves, of deterministic paths, of cause and effect, unfolding with the silent inevitability of a river flowing downhill. This is the giant's world, vast, predictable, and continuous. And here lies the problem. The quantum world, as we have come to know it, is none of those things. It is not smooth. It is quantized, existing in discrete, chunky packets. It is not deterministic. It is probabilistic, a realm of shimmering possibilities that only collapse into one reality upon observation. It is not a silent, flowing river, but a jittery, effervescent sea of energy where particles pop in and out of existence. When we try to unite these two descriptions of reality, the smooth geometric grandeur of general relativity and the grainy, uncertain world of quantum mechanics, the mathematics breaks down. The languages are incompatible. It's as if we have one perfect map for the continents and another perfect map for the oceans. But when we try to stitch them together at the coastline, they tear apart into nonsense. This conflict becomes most severe at the universe's extremes inside the singularity of a black hole, or at the very first instant of the Big Bang. In these places, where immense mass is crushed into an infinitesimal space, both the giant of gravity and the quantum family must coexist. To describe what happens there, we need a single language. We need a theory of quantum gravity. Physicists, in their quest to find this common tongue, have hypothesized a messenger for the giant. If the other forces have their quantum particles, then gravity should have one too. They have even given it a name, the graviton. This hypothetical particle would be the smallest possible packet of gravitational energy, a tiny ripple in the fabric of space-time. It would be massless, like a photon, and travel at the speed of light. It would be the whisper that passes between the sun and the earth, the message that says curve here, curve. But the graviton remains a ghost. The gentle giant is so incredibly gentle, gravity is astoundingly weak compared to the other forces, that its individual messengers are almost impossible to detect. A single graviton would interact so faintly with matter that we would need a detector the size of a planet parked next to a neutron star just to have a chance of spotting one. It is a theoretical necessity, a character demanded by the plot of quantum field theory, but one that has never made an appearance on stage. And so, we are left with this beautiful, aching mystery. The force that shapes the entire cosmos on the largest of scales, the silent architect of galaxies and solar systems, refuses to play by the rules of the very particles it governs. The giant walks through the quantum marketplace, its steps shaping the ground beneath everyone's feet, yet it seems to pay no mind to the frantic buzzing crowd. It speaks in a language of geometry, while they chatter in a language of probability. This is not a failure of physics, but an invitation. It is the edge of the map where the known world gives way to unexplored territory. It reminds us that our most complete theories are still just that, theories. They are stories we tell about the universe, stories that have proven remarkably effective, but are not yet the final word. The problem of gravity is a call to humility and to wonder, a reminder that the most familiar things can hold the deepest secrets. The separation between the world of the giant and the world of the quantum particles seems for now absolute. One governs connection on the grandest scale, binding the universe together with its gentle, inexorable curvature. The other describes the frenetic, isolated lives of particles. But what if connection is a more fundamental aspect of the quantum world than we first imagined? What if the particles themselves are linked in ways that defy our classical intuition, tied together by invisible threads that transcend space itself? What if, on their own scale, they exhibit a form of connection so strange, so immediate that it borders on the magical? Before we can hope to unite the largest scales with the smallest, perhaps we must first understand the deepest connections that exist within the quantum realm itself. We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense, unyielding grip of the strong force, the powerful warden that locks quarks together inside protons and neutrons. And we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change. These are the forces of interaction, the rules of engagement between the particles that make up our universe. They are the messengers, the binders, the agents of change. But what if there exists another kind of connection? Not a force that pulls or pushes, but an intrinsic link, a shared identity that transcends distance and time itself. What if two particles born from the same event could become forever bound in a single shared story, no matter how far apart they travel? This is not a tale of forces, but of an indivisible wholeness, a ghostly tether that hints at a reality far more interconnected than we could ever imagine. To grasp this, let us leave the world of particles for a moment and imagine a simple game of chance. Picture in your hands a very peculiar device. When you press a button, it doesn't produce one coin, but two. These coins are perfectly balanced, but they are linked in a special way. If one lands heads, the other is guaranteed to land tails. They are perfect opposites. Now we place these two coins into a spinner, which sends them flying in opposite directions. You catch one, and your friend standing on the far side of a vast field catches the other. Before you look at your coin, what is its state? You don't know. It could be heads, or it could be tails. It exists in a haze of probability, a 50-50 chance. The same is true for your friend's coin. But quantum mechanics tells us something far stranger. It suggests that until the moment of observation, the coins are not merely unknown. They are, in a very real sense, undecided. The entire system, your coin and your friend's coin together, exists in a single state of potential, a combined state of heads tails and tails heads simultaneously. Now you lift your hand and look. Your coin is heads. In that exact instant, the haze of probability collapses, and not just for you. In that same infinitesimal moment, you know with absolute certainty that your friend's coin is tails. This knowledge seems to arrive instantly faster than any signal could possibly travel across the field. You might think, well, this is simple. It's like putting a black glove in one box and a white glove in another. You shuffle them, send them to opposite ends of the earth. When you open your box and see the black glove, you instantly know the other is white. The information was always there, hidden from you. But this is where the quantum world departs from our everyday logic. The universe, according to countless experiments, does not operate like a pair of gloves. Before you looked, your coin was not secretly heads. Its identity was genuinely unresolved. The act of your measurement didn't just reveal its state. In a profound way, it helped create it. And in doing so, it simultaneously created the state of its distant twin. This is quantum entanglement. And it is this phenomenon that Albert Einstein, one of the architects of this new physics, found so deeply disturbing. He famously called it spukhafte Fernwirkung, or spooky action at a distance. He could not accept that measuring a particle here could instantaneously influence another particle way over there, seemingly breaking the cosmic speed limit, the speed of light. He was convinced that there had to be some hidden information, some local hidden variables like the color of the gloves that the particles carried with them from the start. He believed that the quantum description of reality was incomplete. For decades, this remained a profound philosophical debate. Was the universe truly this strange, or was there a deeper, more classical reality hiding beneath the surface? Then, in the 1960s, a physicist named John Bell devised a brilliant mathematical theorem. It provided a way to experimentally test the difference between Einstein's hidden information idea and the spooky predictions of quantum theory. The experiments were complex, requiring immense precision, but when they were finally performed, the results were unambiguous. Again and again they have shown that Bell was right, and Einstein, in this one instance, was mistaken. The universe is indeed spooky. There are no hidden gloves. The connection is real. Let us be clear about what this means. This instantaneous link cannot be used to send faster-than-light messages. While your measurement instantly determines the state of the distant particle, the outcome of your measurement, heads or tails, is completely random. You cannot force your coin to be heads just to send a 1 to your friend. The universe preserves causality, but it does not preserve our cherished notion of separateness. Entanglement reveals a fundamental truth about reality. At the deepest level, the universe is not a collection of individual isolated objects. It is an inseparable, interconnected whole. Two particles that have interacted can remain part of a single system, a single mathematical description, even if they are separated by light years of empty space. The space between them becomes irrelevant. They are two bodies, perhaps, but they share a single quantum soul. This idea shatters our intuitive picture of the world. We are accustomed to thinking of things as being here or there. We see ourselves as separate from the chair we sit on, from the air we breathe, from the stars in the night sky. But entanglement suggests that this sense of separation is an illusion, a feature of our macroscopic scale. At the fundamental level, there is a web of connection, a subtle and ghostly tapestry that underlies all of existence. The universe, it seems, has a long memory. This profound interconnectedness, this breakdown of simple locality, forces us to ask a deeper question. If particles are not just tiny independent points of matter, but can be part of a vast non-local system, then what are they truly? Our model of them as miniature billiard balls bouncing off one another begins to feel inadequate. It struggles to contain this ghost-like connection across the void. Perhaps our focus on the particle itself has been a distraction. What if the particles are not the fundamental story, but merely symptoms of something else? What if they are just localized vibrations, focused points of energy in a deeper, all-pervading medium that allows for such connections? We have reached the limits of the particle picture. To go further, we must change our perspective entirely and look not at the dancers, but at the dance floor itself. We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense, unyielding grip of the strong force, the powerful warden that locks quarks together inside protons and neutrons. And we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change their very identity. In all these stories, we have spoken of particles of messengers and matter of tiny, distinct actors playing their parts on the cosmic stage. But what if this picture, as beautiful as it is only a shadow of a deeper truth? What if the actors themselves, the electron, the quark, the photon, are not the fundamental reality? What if they are merely momentary expressions of something far more vast, more continuous, and more mysterious? To truly understand the universe, we must now take a gentle step back, allowing our focus to soften and look not at the players, but at the stage itself. For it turns out the stage is not empty space. The stage is the story. Imagine, if you will, a perfectly still and silent ocean stretching in every direction beyond any horizon. It is an ocean of pure potential calm and undisturbed. It has no color, no texture, no sound. It is so perfectly uniform that you would not even know you were in it. It simply is filling every cubic centimeter of the universe, from the space between your fingers to the vast cold darkness between galaxies. This is not an ocean of water, but an ocean of being. This is a quantum field. Now imagine a single tiny disturbance, a focused pulse of energy, a gentle tap on the surface of this infinite, invisible sea. A ripple forms. It is a localized vibrating knot of energy that travels across the calm expanse. This ripple, this fleeting energetic wave, is what we perceive as a particle. An electron is not a tiny solid marble moving through space. An electron is a single localized excitation of the electron field, an ocean that permeates all of reality. When you see an electron, you are not seeing a thing. You are seeing the field doing something. This is the central idea of what physicists call quantum field theory, the most successful and profound description of reality humanity has ever conceived. It tells us that the fundamental building blocks of the universe are not particles. They are these invisible fluid-like fields. And there isn't just one. For every fundamental particle we have discovered, there is a corresponding field, an entire ocean of potential that fills all of space-time. There is an up-quark field, a down-quark field, a muon field, a gluon field. Each one is a separate invisible ocean, interpenetrating all the others, all coexisting in the same space, like different colors of light blending together to form a single clear beam. They are all around us and within us. The very substance of your body is made of localized ripples in the quark and electron fields. The light warming your skin is made of ripples in the electromagnetic field. The universe is not an empty container with a few specks of matter scattered about. The universe is full. It is a plenum, a vast and vibrant symphony of overlapping vibrating fields. This perspective changes everything. Consider the perplexing ability of particles to be created and destroyed. In our earlier picture, an electron and its antimatter twin, a positron, could collide and annihilate, disappearing in a flash of gamma-ray photons. Where did they go? Where did the photons come from? The field perspective makes this process seem natural, almost inevitable. Imagine our electron field again. An electron is a ripple. A positron, its antiparticle, is like a counter-ripple, a dip, where the electron was a crest. When this ripple and this dip meet on the surface of the field, they cancel each other out. The electron field becomes calm again at that location. But the energy cannot simply vanish. The energy of those two vibrations is transferred into a different neighboring field, the electromagnetic field. That sudden input of energy creates two new ripples in that field. And what are ripples in the electromagnetic field? They are photons. The particles did not turn into photons. The vibration simply passed from one medium to another, from one ocean to the next. The energy that once constituted a ripple in the electron field now constitutes a ripple in the field of light. Creation and annihilation are merely the universe's way of shifting energy between these fundamental underlying seas. This also gives us a deeper way to understand the forces. We spoke of particles exchanging messengers like two boats tossing a ball back and forth. But in the language of fields, the interaction is more intimate, more fluid. When an electron, a ripple in the electron field, moves, it naturally disturbs the other fields around it, especially the electromagnetic field. This disturbance propagates outward like the wake from a boat, and this traveling disturbance eventually jostles the electron field somewhere else, causing another ripple to move. What we call a force is not a projectile being thrown, but the coupled trembling of interconnected fields. The universe is a dynamic tapestry where a pull on one thread sends vibrations shimmering through the whole cloth. Let this new reality settle in. The world is not made of tiny solid things. It is made of potentialities, of invisible oceans of existence. What we call empty space is in fact a bubbling cauldron of these quantum fields in their lowest energy state, a silent sleeping sea. What we call matter is when these fields are awakened, when they are plucked like a string and begin to vibrate. You are not a collection of objects. You are a complex, stable pattern of vibrations. You are a song being played on the instruments of these cosmic fields. This view dissolves the hard line between a particle and the space it occupies. The particle is a state of space. It is a behavior of the field that is everywhere. There is a deep and profound unity here. Every electron in the universe, from one in a distant star to one in the tip of your finger, is a ripple in the very same universe-spanning electron field. They are all connected, all born from the same fundamental substance. And yet, a crucial question arises from this beautiful unified picture. If all particles are just excitations in these universal fields, why are they so different? A ripple in the electromagnetic field, a photon, is weightless and travels at the ultimate cosmic speed limit. But a ripple in the electron field has a distinct small mass. A ripple in the top quark field is extraordinarily heavy. Why is this? If they are all just vibrations, what gives these vibrations the property we experience as inertia, as weight? Why do some ripples seem to glide effortlessly across their fields, while others seem to move as if through thick molasses? It suggests that our tour of these fundamental oceans is not yet complete. There must be one more field, one we have not yet named. A field of a completely different kind, not associated with matter, or a familiar force, but one whose entire purpose is to interact with the other fields, granting their vibrations the very quality of mass. There must be a universal medium that creates a drag, a resistance to motion for some particles, but not for others. To understand where mass itself comes from, we must now turn our attention to this final, most mysterious ocean. We must seek the giver of mass. We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense unyielding grip of the strong force, the powerful warden that locks quarks together inside protons and neutrons. And we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change their very identity. But in our journey through this realm of messengers and mediators, a profound and troubling question has been quietly waiting. The photon, the carrier of light, is utterly massless. It is pure energy traveling unimpeded at the cosmos's ultimate speed limit. Yet the carriers of the weak force, the W and Z bosons, are titans. They are among the heaviest fundamental particles ever discovered, nearly 100 times more massive than a proton. How can this be? Both are messengers of fundamental forces, born from the same quantum logic, described by equations that whisper of a deep underlying symmetry. Why would nature bestow such immense heft upon one and grant the other complete freedom from it? What is this quality we call mass, and from where does it come? For decades this was not just a question. It was a crack in the very foundation of our understanding. The elegant mathematics of the Standard Model worked beautifully, but only if its force-carrying particles were massless. Yet reality disagreed. The scales of the universe were clearly unbalanced, and no one knew who or what was putting its thumb on the ethereal scale. The answer, when it was finally pieced together, was as radical as it was elegant. It required imagining something that is everywhere, yet is nowhere to be seen. It asked us to believe that the vacuum of space is not truly empty. Imagine for a moment that the entire universe, every cubic centimeter of space from the core of the Earth to the most distant intergalactic void, is permeated by an invisible, intangible field. It isn't a substance like water or air. It is a property woven into the fabric of space-time itself, a universal presence. This is the Higgs field. Now picture this field not as an empty stage, but as a grand crowded ballroom. The people in this room represent the Higgs field filling the space from wall to wall. A fundamental particle traveling through the universe is like a person trying to cross this room. And here the story divides. A particle like the photon is like a person who is utterly unknown to the crowd. It slips between the people unnoticed and unhindered. No one turns to look. No one tries to speak to it. It can move through the room as if it were empty, traveling at the fastest possible speed. Because it does not interact with the field, it has no mass. But now imagine another person entering the room, someone famous, a celebrated scientist, or a beloved artist. As this person tries to cross people in the crowd, turn. They cluster around wanting to ask a question, to shake a hand, to share a word. A small group forms, and it moves with the person. Their journey across the room is now sluggish. They are harder to get moving, and harder to stop once they are in motion. This resistance to a change in motion, this drag imposed by the interacting crowd, is precisely what we perceive as mass. The particle hasn't changed its intrinsic nature, but its journey through space is now fundamentally different. It has acquired mass from its interaction with the Higgs field. This is the essence of the Higgs mechanism. Particles are not born with mass. Mass is not a label they carry, but a relationship they have. It is a measure of how strongly they couple to this universal, invisible field. An electron, for instance, is like a minor celebrity. It gathers a small, persistent entourage as it moves, and so it has a small mass. The mighty top quark, on the other hand, is the most famous figure imaginable. Its interaction with the field is so immense that it is burdened with a colossal mass, making its journey through space like wading through thick cosmic molasses. And the W and Z bosons, the messengers of the weak force, interact very strongly indeed. The crowd of the Higgs field clings to them, granting them their great weight, and in doing so, restricting the range of their force to the tiny confines of the atomic nucleus. The massless photon, by contrast, feels no such drag, and so the reach of its electromagnetic force is infinite. The beautiful symmetry of the forces is not broken. It is merely hidden by the presence of this field. For nearly 50 years, this was a beautiful, compelling theory. But how could you prove that an invisible, all-pervading field truly exists? The answer was to try and excite it. If you could strike the field with enough energy, you might create a ripple in it, a particle. Return to our crowded ballroom. Imagine someone at the doorway shouts a fascinating rumor into the room. The people nearby will cluster together to hear it, then move to tell their neighbors, who will cluster and move on in turn. A knot of people, a localized clump of interaction, will travel across the room. This moving transient cluster is not one of the individuals in the room. It is an excitation, of the room itself. This is the Higgs boson. It is the physical proof, the tangible evidence that the field is real. For years at the Large Hadron Collider, physicists smashed particles together at nearly the speed of light, pouring unimaginable amounts of energy into a single point in space. They were in effect shouting into the vacuum, hoping to hear an echo. And in 2012 they did. They detected a new particle, a fleeting ripple with the precise properties predicted decades earlier. The rumor in the ballroom had finally been heard. The giver of mass had revealed itself. This discovery changed our perception of reality. The solid world we touch is solid not just because of the properties of its atoms, but because its fundamental constituents are caught in a constant silent dialogue with the cosmos. The weight you feel in your own body, the inertia of a planet in its orbit, the very possibility of complex structures forming at all, is owed to this invisible field that filled the universe in its infancy. Without it, all particles would be massless, zipping past each other at the speed of light. The universe would be a thin, frantic soup of energy, incapable of forming atoms, stars, or galaxies. There would be no structures, no planets, and no life to ponder its own existence. The Higgs field, then, is not just another part of the quantum tapestry. It is the loom upon which much of the universe's substance is woven, and its arrival marks a pivotal chapter in the cosmic story. For this field was not always active. In the first impossibly hot and dense moments of creation, the universe was a place of perfect symmetry. The field lay dormant, and all particles were massless equals. But as the infant cosmos expanded and cooled, it reached a critical temperature, a moment of profound transformation. Just as steam condenses into water, the Higgs field condensed out of the energetic vacuum, and in a fraction of a second, it flooded all of space. In that instant, mass was born. The universe underwent its first and perhaps most fundamental phase transition. To understand our world today, we must therefore look back to that dawn, to listen for the echoes of that first formative moment. We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense unyielding grip of the strong force, the powerful warden that locks quarks together inside protons and neutrons. And we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change their very identity. We have studied the laws that govern the infinitesimally small. Now let us turn our gaze to the infinitely large and to the most distant past, for it is there in the crucible of the first moment that these fundamental rules wrote the story of everything. Let us embark on a journey backward in time. Imagine the great tapestry of cosmic history woven over 13.8 billion years now being unspooled before you. We pull on a thread, and time begins to flow in reverse. The galaxies, scattered like jewels on black velvet, cease their lonely expansion and begin to rush back toward a common center. Great clusters of galaxies merge the space between them, shrinking away. The stars themselves, shining beacons in the cosmic night, dissolve back into the vast, swirling clouds of hydrogen and helium from which they were born. These clouds grow hotter and denser, their gentle glow intensifying into a brilliant uniform haze that fills all of space. We are now just a few 100,000 years after the beginning. There are no stars, no galaxies, only a searing opaque fog of plasma. Protons and electrons, not yet bound into atoms, dart about in a chaotic dance, trapping light and preventing it from traveling freely. The universe is a brilliant, featureless wall of light. But as we continue our journey backward, this plasma grows hotter still, and the structures within it begin to break down even further. We arrive at a point only 3 minutes after the first moment. The universe is now so hot and so dense that even atomic nuclei cannot hold themselves together for long. The helium and hydrogen nuclei that would one day fuel the stars dissolve into their constituent parts, a seething soup of protons and neutrons batted about by a storm of photons and neutrinos. Here in this primordial furnace, the weak and strong forces are in a frantic battle fusing particles together, only for the sheer energy of the environment to blast them apart again. The very building blocks of matter are being forged and reforged second by second. But we must go further, back past the first second, into the first microsecond of existence. And here, something extraordinary happens. The temperature has become so immense, the pressure so unimaginable, that even the protons and neutrons themselves can no longer exist. The unyielding grip of the strong force which binds quarks in sets of 3 is finally overwhelmed. The quarks and their loyal messengers, the gluons, are set free. We have arrived at the shore of a primordial ocean, the quark-gluon plasma. In this state, the universe is a perfect incandescent liquid of its most fundamental ingredients. There are no atoms. There are no protons. There is only a shimmering chaotic sea of free quarks, antiquarks, and gluons, all moving at nearly the speed of light, a substance so extreme that it has only been recreated on Earth for the briefest of instants inside the most powerful particle accelerators. This is the universe as a pure quantum system where the rules of particle physics are not just a description of reality, but the only reality there is. Our journey is not yet over. We must press on into the first tiny fractions of a microsecond, a sliver of time so small it defies human intuition. Here the energy is so high that the forces themselves begin to change their character. We learned of the electromagnetic force and the weak force as distinct entities, one carried by photons, the other by W and Z bosons. But in the extreme heat of this first moment, this distinction vanishes. The two forces merge into a single unified entity, the electro-weak force. It is as if water and ice, two very different forms of H2O, were revealed to be one and the same in a world hot enough that ice could never form. As the universe expanded and cooled, this unified force froze out, fracturing into the two separate forces that orchestrate so much of our world today. Physicists believe that if we could go back even further, to even higher energies, the strong force, and perhaps even gravity itself, would also merge into one grand unified superforce, the single elegant principle from which all the complexity of the cosmos emerged. And it is here in this primordial soup of unified forces and fundamental particles that we encounter the deepest mystery of our existence. In these first moments, energy was constantly converting into pairs of matter and antimatter particles, an electron and its antimatter twin, the positron, a quark and an antiquark. For every particle of matter created an equal and opposite particle of antimatter should have been born. As the universe cooled, these pairs should have found each other and annihilated, converting back into pure energy, leaving behind a cosmos filled with nothing but light, a vast, beautiful, but utterly empty universe. And yet, we are here. You are here. The earth beneath your feet, the air in your lungs, the stars in the night sky, all are made of matter. The annihilation was not perfect. Somehow, a slight imbalance occurred. For every billion particles of antimatter, it is believed there existed 1,000,000,001 particles of matter. After the great annihilation was over, that single lonely survivor in every billion pairs was left over. From that cosmic remnant, that tiny statistical error, every star, every galaxy, every planet, and every living being was born. Our entire universe is a monument built from the leftovers of a great cosmic fire, a testament to a fundamental asymmetry that we still do not understand. And so, the visible cosmos is the beautiful result of this imbalance. The matter that survived, clumped together, pulled by gravity to form the magnificent structures we observe through our telescopes. But as we look out at these structures, the graceful spinning arms of galaxies, the majestic waltz of galactic clusters, we find they are moving in ways we cannot explain. They seem to be held in the grip of a gravity far stronger than all the luminous matter we see can possibly account for. It is as if the universe we have so carefully described is only the visible part of the story, a mere wisp of light in an enormous unseen ocean. We are left to wonder, what is this invisible scaffolding that holds our cosmos together? What is this ghost in the machine? We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense, unyielding grip of the strong force, the powerful warden that locks quarks together inside protons and neutrons. And we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change. It is a complete and beautiful picture, a standard model that accounts for nearly every particle interaction we have ever observed. But what if this kingdom, in all its intricate glory, is merely a collection of small, brightly lit islands in a vast, dark ocean? What if the matter we know, the substance of stars, planets, and ourselves, accounts for only a tiny fraction of what truly exists? We now turn our gaze away from the familiar light of the quantum realm and into the profound shadows of the cosmos, where an unsolved mystery awaits. This is a cosmic detective story, and the case begins not with a sound or a flash of light, but with an anomaly in the graceful, silent waltz of the galaxies. In the 1970s, an astronomer named Vera Rubin was patiently observing the Andromeda Galaxy, our great cosmic neighbor. She was measuring how fast its stars were moving, expecting to find a simple pattern. Just as planets closer to our sun move faster than those farther away, she expected stars near the galaxy's bright, dense center to be moving much faster than the lonely stars wandering at its faint outer edges. The logic was simple. Most of the galaxy's visible mass, its stars' gas and dust, is concentrated in the middle. Therefore, the gravitational pull should be strongest there and weakest at the periphery. But that is not what she found. The stars on the outer rim of the galaxy were moving just as fast as those near the center. They were moving far too quickly. At such speeds, they should have been flung off into the blackness of intergalactic space, like children flying off a merry-go-round that is spinning out of control. Yet there they were held in a stable, perfect orbit. The only possible explanation was that some immense unseen source of gravity was holding them in place. The visible matter of the galaxy was not enough. There had to be a vast invisible halo of something surrounding the entire galaxy, its gravitational influence extending far beyond the reach of the last starlight. It was the first footprint of a ghost, the first piece of evidence for what we now call dark matter. This was not an isolated case. Astronomers turned their telescopes to other galaxies, and then to entire clusters of galaxies, and found the same story repeated everywhere. The universe was behaving as if it were 5 times heavier than all its visible matter could account for. A second independent line of evidence soon confirmed this strange conclusion, and it came from Einstein's own theory of relativity. Einstein taught us that massive objects warp the fabric of space-time, and that this curvature is what we experience as gravity. Light, as it travels through the universe, must follow these curves. So a very massive object like a galaxy cluster can act as a cosmic magnifying glass, bending the light from more distant objects behind it. This effect is called gravitational lensing. When astronomers looked at the light from the most ancient, faraway galaxies they saw, it was being distorted, stretched, and magnified in ways that could not be explained by the visible matter alone. The light was being bent by enormous invisible clumps of mass, their gravitational signatures clear and unambiguous. It was like seeing the distortion in the air above a hot road on a summer's day. You cannot see the heat itself, but you can see its effect on the light passing through it. In the same way, we cannot see dark matter, but we can see the way it bends and warps the light of the cosmos. The ghost silhouette was now visible against the backdrop of the oldest light in the universe. So the case is clear. An invisible substance, a form of matter that does not shine or reflect or absorb light, provides the vast majority of the gravitational scaffolding of our universe. But what is it? The investigation immediately rules out all the usual suspects. It cannot be vast clouds of dust and gas, because those would absorb light and be detectable. It cannot be a universe filled with black holes or dim dead stars, because we would be able to detect them through other means, and there simply aren't enough of them. This ghost is not made of protons, neutrons, or electrons. It is not made of any of the familiar particles in our standard model. It must be something new, something entirely outside our carefully constructed quantum kingdom. This is where the cosmic detective story, written in the stars, becomes a quest for particle physicists deep underground. The leading suspect is a hypothetical particle with a wonderfully descriptive name, a WIMP, which stands for Weakly Interacting Massive Particle. Let's break that down. Massive means that while each individual particle might be heavy, perhaps 100 times more massive than a proton, there are so many of them that their combined mass gravitationally dominates the universe. Weakly interacting is the key to its ghostly nature. It means that these particles feel the force of gravity, and they likely interact through the weak nuclear force, but they do not feel the electromagnetic or strong forces. Because they ignore electromagnetism, they cannot emit or absorb light, making them completely dark. Because they ignore the strong force, they do not clump together into nuclei. They pass through ordinary matter, through our planet, through our bodies, as if it were not there at all. Billions of these particles are likely streaming through you right now, silent and unnoticed. The hunt is on. In laboratories buried deep beneath mountains, shielded from the confusing noise of cosmic rays, scientists have built the most sensitive detectors imaginable. They are vats of ultra-pure liquid xenon, or germanium crystals, cooled to near absolute zero, waiting in perfect stillness and silence. They are listening for a whisper in the dark, the faintest possible ping of a single dark matter particle, bumping into one of their carefully arranged atomic nuclei. It is one of the most difficult experiments ever conceived to search for a ghost that barely interacts with our world at all. This invisible matter forms a vast, intricate cosmic web, a filamentary structure stretching across billions of light years. The galaxies we see, these brilliant islands of light, are not scattered randomly. They are formed in the densest nodes of this dark matter web, like dewdrops forming on a spider's silk. Dark matter is the silent architect of the cosmos, the unseen foundation upon which everything we know and love has been built. For decades, physicists believed the story of the universe was a grand cosmic tug-of-war between the outward momentum of the Big Bang and the inward pull of gravity, a pull now understood to be dominated by this dark matter. But in the dying light of the 20th century, a new observation turned this simple story on its head. The universe, it turned out, was not slowing down. It was speeding up. Something was pushing. A strange anti-gravitational force was accelerating the expansion of the void itself, a phenomenon even more profound and perplexing than the ghost we have been chasing. The search for the ghost in the cosmos now leads us to the mystery of the expanding void. We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense unyielding grip of the strong force, the powerful warden that locks quarks together inside protons and neutrons, and we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change. These forces are the architects of structure. They pull, they bind, they hold reality together. But if we quiet our minds and listen to the cosmos on its grandest scale, we can begin to hear a different sound, not a force that pulls, but a presence that pushes. It is like a slow, deep cosmic exhalation, a gentle pressure that is steadily, inexorably driving everything apart. For most of the 20th century, the story of the universe was a story of a great cosmic battle. In one corner stood the explosive momentum of the Big Bang, the outward rush that sent all matter flying. In the other corner stood gravity, the universe's great collector, patiently pulling on every galaxy, every star, every atom, trying to slow the expansion down. The central question was simple: which would win? Would gravity eventually halt the expansion and pull everything back together in a big crunch? Or would the momentum win out, allowing the universe to expand forever, but at a slower and slower rate, like a ball thrown into the air that never quite comes down? For decades, astronomers built their telescopes and pointed them at the heavens, trying to measure the precise rate of this cosmic slowdown. Then, at the very end of the century, two separate teams of astronomers were studying distant spectacular events, type Ia supernovae. These are ancient dying stars that explode with a known standardized brightness, making them perfect cosmic lighthouses. By measuring how faint their light appears to us, we can calculate how far away they are. By measuring how much their light has been stretched, or redshifted, we can calculate how fast they are moving away from us. They were peering deep into the past, expecting to see a universe that was expanding faster long ago than it is today, clear evidence of gravity's braking effect. But they found the opposite. The distant lighthouses were even fainter than they should have been. It was as if they had been carried away from us by a current that was speeding up. The universe was not slowing down. Its expansion was accelerating. This was a discovery that shook cosmology to its core. The great cosmic battle was not what we thought. There was a third contestant in the ring, a hidden influence that was not just resisting gravity, but overpowering it on the largest of scales. This mysterious, repulsive force was given a name as humble as it was profound, dark energy. It is not energy in the way we usually think of it, nor is it dark in the sense of being ominous. It is dark because it is completely invisible and unknown. It does not seem to clump together like matter. It doesn't interact with light. Instead, it appears to be a property of space itself. It is an intrinsic background energy woven into the very fabric of the void. Think of it as a form of anti-gravity, a gentle, persistent pressure inherent in space-time. As the universe expands, more space is created. And as more space is created, more of this energy comes into being, adding to the outward push. It is a quiet, self-reinforcing process. While gravity's pull weakens as galaxies move farther apart, the push of dark energy inherent in every new volume of space remains constant or even grows stronger. The cosmic exhalation is getting deeper. Where could such a strange energy come from? The most promising and most troubling candidate came from the world we have just explored, the quantum realm. As we've learned, the quantum vacuum is not truly empty. It is a seething, effervescent soup of virtual particles that flicker in and out of existence in timescales too short to measure directly. This constant quantum activity, this faint background hum of reality, should imbue every cubic centimeter of space with a certain amount of energy, of vacuum energy. When Albert Einstein first wrote his equations for general relativity, he included a term he called the cosmological constant, a kind of fudge factor to keep his model of the universe static. He later called it his biggest blunder when the universe was proven to be expanding. But with the discovery of acceleration, his constant was revived. Perhaps this quantum vacuum energy was the physical reality behind his mathematical term. Perhaps this was the source of dark energy. It seemed a perfect marriage between the very small and the very large. The energy of the quantum foam could be the engine driving the expansion of the cosmos. Physicists set out to calculate the theoretical energy density of the quantum vacuum based on what we know about particle physics. And when they did, they arrived at a number. Astronomers, meanwhile, calculated the amount of dark energy needed to explain the cosmic acceleration they had observed. They too arrived at a number. And here, what should have been a moment of triumph became one of the deepest paradoxes in all of science. The two numbers did not match. They didn't even come close. The theoretical energy of the vacuum was orders upon orders of magnitude larger than the observed energy driving the expansion. The discrepancy is a 1 followed by 120 zeros. It is a number so vast it is difficult to describe with any metaphor. It is like predicting a hurricane with the force to tear planets from their orbits, and then measuring a gentle breeze that can barely stir a leaf. This colossal mismatch is known as the cosmological constant problem, and it has been called the worst theoretical prediction in the history of physics. It tells us that our understanding of gravity or quantum mechanics, or the very nature of the vacuum, is profoundly, fundamentally incomplete. So we are left suspended between two great mysteries. We look out into the cosmos and see the evidence of this gentle, relentless push. We see the galaxies flying away from us faster and faster, their light fading as they recede into the expanding void. We can imagine a far distant future where this cosmic breath has pushed every other galaxy beyond our horizon, leaving our own Milky Way as a solitary island in an endless cold, dark sea. And when we look down into the equations that describe the fabric of that void, we find an energy source that is paradoxically both too powerful and too weak a ghost in the machine of our theories. Our entire portrait of this grand expanding cosmos, from the faint energetic hum of the quantum vacuum to the cold distant light of a dying star, is built upon a single foundational act. It is built upon the act of looking, of measuring, of observing. The universe only reveals its accelerating nature when we capture its ancient light and interpret its message. The paradox only emerges when we compare our theories of the unseen with the results of what we have seen. We have gazed outward to the very edge of space and the ultimate fate of reality. Now we must turn our gaze inward. We must explore the subtle, powerful, and mysterious relationship between the universe and the one who observes it. For it is in that delicate meeting that our reality takes shape. We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense, unyielding grip of the strong force, the powerful warden that locks quarks together inside protons and neutrons. And we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change. We have learned the rules of the game, the fundamental grammar of existence. But now, we arrive at the edge of the known at a quiet, misty shore, where the rules themselves seem to grow soft and uncertain. It is a place where a profound question hangs in the air, a question not about what things are, but about what it means to know them. For in the quantum realm, the act of looking is not a passive one. The observer is never just a spectator. To measure, to ask to see, is to participate. And in that participation, we cast a shadow that falls across reality itself. Imagine an electron alone in the void. Before we try to find it, quantum mechanics tells us it does not have a single definite location. Instead, it exists as a wave of potential, a shimmering cloud of probability. It is a haze of maybes spread out across space. It has a certain chance of being here and a certain chance of being there, but it is definitively in no single place. This is the state of superposition, a ghostly existence where all possibilities coexist at once. Yet the world we experience is not a haze of maybes. Our chairs are solid. The moon has a definite position in the sky. When we look for the electron, we always find it in one spot. The moment our instrument interacts with it, the entire cloud of probability vanishes, collapsing instantly into a single concrete point. The wave becomes a particle. The maybe becomes an is. This is the measurement problem, perhaps the deepest and most unsettling mystery in all of science. What is this magical act called measurement? What is the line between the quantum world of potential and the classical world of certainty, and who or what gets to draw it? To bring this question out of the abstract and into the stark light of our imagination, the physicist Erwin Schrödinger devised a thought experiment. It is a strange and famous parable, not of cruelty, but of profound ambiguity. Imagine a sealed soundproof box. Inside, there is a cat. Alongside the cat is a tiny piece of radioactive material, an atom so unstable that in the next hour there is exactly a 50% chance it will decay and a 50% chance it will not. If the atom decays, it releases a particle that triggers a Geiger counter. The Geiger counter, in turn, is connected to a small hammer. If triggered, the hammer will shatter a vial of poison, and the cat will die. The box is closed. The hour begins. Outside, we wait. Inside, the quantum world is about to connect with our own. The fate of a living creature is tied to the probabilistic whim of a single atom. According to the strange rules we have learned, as long as the box remains closed, the atom is in a superposition. It has both decayed and not decayed simultaneously. But because the entire system is linked, this quantum uncertainty scales up. The Geiger counter is both triggered and not triggered. The hammer is both fallen and not fallen. The vial is both shattered and intact. And the cat, therefore, must be in a superposition of being both alive and dead. This is not a riddle. It is the logical conclusion of applying quantum rules to a system we can understand. It is designed to feel absurd to show us the chasm between the two realms. A cat is not a wave of probability. A cat is either alive or it is not. So where does the quantum description fail and the classical one take over? The answer hinges on that simple final act, opening the box. The moment we do, the superposition ends. We will find either a living cat or a dead one. The universe will have picked a single reality from the two possibilities. But when did it choose? Was it when the atom interacted with the Geiger counter? Was it when the light from inside the box reached our eyes? Or, in the most unsettling version of the question, was it only when a conscious mind registered the outcome? This is the shadow of the observer. For decades, the dominant answer was the Copenhagen interpretation championed by Niels Bohr. It is a pragmatic, almost stoic view. It tells us that it is meaningless to ask what the cat's state was before we looked. The quantum world is simply not real in the way we think of reality. It is a set of probabilities, and the act of measurement forces one of those probabilities to become history. The wave function collapses because we looked. That's all we can say, and all we need to say. But for some, this was deeply unsatisfying. It felt like sweeping the universe's greatest mystery under the rug. And so another far more staggering idea emerged. This is the many worlds interpretation. It proposes that the wave function never collapses at all. The universe does not choose. Instead, it splits. When you open the box, reality itself cleaves in two. In one universe, you open the box and find a living purring cat. In another parallel universe, an identical version of you opens an identical box and mourns a cat that has died. Both outcomes happen. Every quantum possibility branches off into its own separate, real, and complete universe. The cosmos is not a single story, but an infinitely branching tree of stories, and we are living on just one of its countless boughs. We do not know which of these interpretations, if any, is correct. Modern physics has added another layer of understanding, a concept called decoherence. which suggests that a quantum system loses its strange properties as soon as it interacts with a large complex environment like a Geiger counter or a cat. The measurement is not a special act, but a natural consequence of entanglement with the wider world. The system leaks its quantum nature into its surroundings. Yet even this does not fully erase the philosophical shadow. It tells us how the choice is made, but not which choice is made, or why. We experience only one. Perhaps the very question is framed the wrong way. The great physicist John Archibald Wheeler suggested that we live in a participatory universe. Our acts of observation, the questions we choose to ask, are not passive inquiries about a pre-existing reality. They are creative acts that help bring that reality into being. The universe, at its most fundamental level, may not be a great machine we are looking at, but a great conversation we are a part of. We are not just seeing the story. We are in some small, inexplicable way helping to write it. And so, we find ourselves here at the end of our journey through the forces and particles, facing not an answer, but a profound and humbling mystery. We have seen the machinery of the cosmos, the elegant dance of quarks, and the brilliant flash of photons. We have learned the laws that bind the whole of creation together. But the final lesson may be this: the universe is not a static object of study. It is a dynamic unfolding process, and we are not outside it. The shadow of the observer is simply the mark of our own intimate connection to all that is. It is the final crucial thread we must hold in our hands as we now step back, ready at last to see the whole design. For it is only by understanding our place within it that we can begin to truly appreciate the breathtaking beauty of the entire quantum tapestry. We have walked through the bustling, vibrant kingdom of the quantum world, meeting the three forces that govern its every interaction. We have seen the brilliant messenger of light, the photon, carrying the electromagnetic force that binds atoms and paints our world with color. We have felt the immense, unyielding grip of the strong force, the powerful warden that locks quarks together, inside protons and neutrons. And we have witnessed the subtle alchemy of the weak force, the quiet transformer that allows stars to shine and elements to change their very identity. We have examined one by one the threads of reality. Now it is time to take a step back. Imagine we are standing in a great hall before a tapestry of truly cosmic proportions. For our entire journey, we have been standing with our faces pressed close to the fabric, tracing each individual fiber, marveling at the strength of a single knot, the shimmer of a particular color. We have learned the names of the threads, the quarks, the leptons. We have studied the patterns of the weave, the strong, weak, and electromagnetic forces. This intimate knowledge is the foundation of everything. But to truly appreciate the artist's vision, we must now move away from the detail and behold the whole design. This grand design, this magnificent and coherent picture, is what physicists call the standard model of particle physics. It is not merely a collection of facts or a list of particles. It is one of humanity's greatest intellectual achievements, a story told in the language of mathematics that describes all the known matter in the universe and 3 of the 4 ways it interacts. It is a testament to generations of curiosity of brilliant minds in quiet rooms, of vast collaborations spanning the globe. With breathtaking accuracy, this model can predict the outcome of particle collisions, explain the glow of a distant star, and describe the fundamental architecture of the chair you sit in and the air you breathe. The tapestry it reveals is consistent, elegant, and profoundly beautiful. Every particle we have met, from the steadfast up quark to the ghostly neutrino, has its perfect place. Every force a precise and predictable role. It is a masterpiece of order, woven from the chaos of the quantum foam. And yet, as our eyes adjust to the grand scale of the tapestry, we begin to notice things. The design is vast, but it does not cover the entire wall. There are sections that are strangely blank and edges that seem to fray into nothingness. We see that for all its beauty, our tapestry is incomplete. Our gaze is drawn first to the shadows. In the patterns of the cosmos, in the graceful spin of galaxies, and the clustering of galactic superstructures, astronomers have seen the unmistakable pull of gravity where there should be none. The visible matter, the stars, the gas, the dust, all the familiar threads we have so carefully catalogued, is not enough. There is something else out there, something 5 times more abundant than all the atoms in the universe combined. We call it dark matter. It is a part of the tapestry, but it is woven from an invisible thread. It does not shine, it does not reflect, it does not absorb light. It is a silent, gravitational ghost. Its presence felt only by the way it bends and shapes the fabric of space-time around it. The standard model, for all its glory, has no thread to account for it. It is a profound and humbling mystery, a reminder that the universe we can see is only a small fraction of what truly exists. Then, as we continue to gaze, we notice something even more astonishing. The tapestry is not static. The entire fabric is stretching, expanding, as if the loom itself is growing. And the most perplexing part is that this expansion is accelerating. Something is pushing the universe apart, a gentle but relentless pressure embedded in the vacuum of space itself. We call this dark energy. It is not a force in the way we have come to understand forces. It is not a particle. It seems to be a property of space itself, a quiet, insistent energy that drives the cosmos toward an ever more distant and lonely future. In our tapestry, this would be like discovering that the empty space between the threads has a character all its own, a dynamic quality that dictates the ultimate fate of the entire design. The standard model offers no explanation for this either. It is the deepest mystery in all of science, a fundamental feature of our reality that we have only just begun to perceive. Finally, we look at the very foundation of the weave itself. Our quantum story, the story of the threads, is a masterpiece. And we have another great story in science, Einstein's theory of general relativity, which is the story of space-time, the loom upon which the tapestry is woven. It describes gravity as the curvature of this fabric, a beautiful geometric dance of mass and energy. Both theories work perfectly in their own domains, quantum mechanics, for the very small, general relativity, for the very large. But when we try to bring them together, where the universe is both incredibly massive and incredibly small, like in the heart of a black hole, or at the moment of the Big Bang, the mathematics breaks down. The two grandest stories our species has ever told refuse to speak the same language. The thread of gravity, the fourth and most familiar force, has not yet been successfully woven into the quantum tapestry. Finding the theory of quantum gravity is the holy grail of modern physics. The search for the master pattern, the single unified principle that describes the loom and the thread as one inseparable reality. And so we stand here in this great hall of understanding, before a work of breathtaking genius that is still profoundly a work in progress. We are not at the end of a story, but rather at the end of a single chapter. The journey through the quantum world does not leave us with a sense of finality, but with a feeling of profound humility and boundless wonder. It teaches us that the universe is not obligated to conform to our intuition. Reality at its most fundamental level is a place of probability waves of particles that are also fields of connections that defy space and time. It is stranger, more interconnected, and more elegant than we could ever have imagined. The tapestry is not just something we observe. We are woven from it. Every atom in our bodies, every spark of consciousness in our minds is a testament to the dance of these particles and forces. We are the universe's way of looking back at itself, of trying to understand its own intricate design. The frayed edges and the dark, empty spaces are not failures. They are invitations. They are the frontiers of human curiosity, the next great chapter waiting to be written, the next thread waiting to be discovered. The beauty of the tapestry lies not only in the parts we understand, but in the vast shimmering mystery of what still lies beyond our sight. And so our journey concludes not with an answer, but with a deeper appreciation for the question. To be alive in this universe is to be a part of this unfolding story, a brief, wondrous opportunity to gaze upon the cosmic tapestry and add through our own curiosity and courage a single humble stitch to its magnificent, unfinished edge. As you close your eyes, may you carry with you not just the knowledge of particles and forces, but the quiet awe of existence itself, the simple, staggering beauty of being a conscious part of it all.